I will just rapidly share my screen to show you the program. So we will have nearly a 3-hour program. I am sorry, I completely forgot to make a break, but you can do a break whenever you want. So there will be first talks about, let us say, focus on Astro Seismology. I tried to have somebody from observations of subgiants, but I didn't succeed to attract them here. But there will be very interesting talk by Gaël, by Sébastien Salmon on Astro Seismology, especially, and modeling. Then there will be the talk by Norbert, Massive Stars. Volker is not yet connected. Lionel will speak about supermassive stars, Miguel about the rotation in the very late phases of stars during the supernova explosion. And Chris will speak more about population synthesis. And Hank, I had to put you at the end because the program was already done. I could not change anything at a given point. So it was the only possibilities to add you, even if you would have been better at the beginning, I would say, to introduce a subtopic. I am very sorry for that, but you know, it's a kind of organization where I am not all the powers at hand, let us say.
Yeah. I should apologize for squeezing in and reducing the time for all of the others.
Okay, so hello, Volker. Nice to meet you. Dear George, I have, and okay, very well. So I think that I welcome you all. We shall begin immediately now. Thank you all for having accepted to participate to this sharing of material, of ideas, of talks about stellar rotation. And I will give immediately the floor to Gaël, who will present the first talk of this parallel session, the internal rotation of low mass stars from solar and stellar astro seismology. So please, Gaël.
Thank you, Georges. Thank you for the introduction. I'll try to put the PDF in presentation mode so you can see better the slides. Do you see the slides correctly?
Yes.
Okay, very nice. So, well, yes, as you can see, I'll talk about solar and stellar seismology and how it can constrain the internal rotation of low mass stars. So first, a low mass star, what I will call a low mass star, will be a star that exhibits an outer convective envelope during its main sequence. So the surface will undergo magnetic braking, and of course the core will contract as the star evolves, and the angular momentum redistribution inside the star will occur through both hydrodynamical and magnetic processes. A key feature that we have to keep in mind here is that the evolutionary phases are relatively long. The main sequence, it's a few gigayears. Shell hydrogen burning is about 1 gigayear. So the processes have time also to act during these relatively long evolutionary phases. And to get access to rotation, for the surface rotation, you can have access to it through spots or through V-sin I measurements, or for the internal rotation, I would say the only way and the best way would be through solar for the sun and stellar for the stars seismology. So it's the observations of global standing waves or oscillations inside stars that you can use to characterize the internal structure and the internal rotation. So for Astro Seismology, I refer you to the seminal book by Uno and collaborators if you want to see the formalism, etc., etc. And of course, a key feature is also, depending on the evolutionary stage, you will see different physical modes, different physical nature of the oscillations, and you will have access to different information. Of course, also the quality of the data, like for example, comparison, the duration of the observations will be also a key factor in what you will be able to do in terms of rotation. So the formalism for low mass stars, we're talking about usually slow rotators, and a perturbative approach can be used for the inference problem of the internal rotation. So it's a bit like introducing the Zeeman effect in quantum mechanics. For the stellar oscillation problem, in the non-rotating case, you have only two quantum numbers identifying the eigenvalue, so the radial order and the angular degree. As soon as you introduce rotation, you lift a degeneracy, you break a symmetry, and you have then a third quantum numbers that characterizes the oscillations, the azimuthal order. And observationally, what happens is that instead of having a degenerate peak in the oscillation spectrum, you see multiplets They respect, of course, quantization rules. So here it's a dipolar mode, so L equal 1, and you will have m plus 1, 0, and minus 1 that will be allowed, and you will see them in the oscillation spectrum. And from the spacing between the peaks, you will be able to measure what we call a rotational splitting, and you will use this rotational splitting to solve this integral equation here that relates the splittings to the internal rotation profile. The physical nature of the mode is hidden in the kernel function, some sort of a weight function that appears in this integral. And basically, depending on the mode you see, you will have access to different regions inside the star. For example, here I show you kernels for a solar model. The purple, red, and blue curves are associated to kernels of gravity mode. So you see a high amplitude in the core, very low amplitude at the surface, whereas the orange and green curves are associated to kernels of acoustic oscillation, so-called P mode, and you have a high amplitude at the surface and a rapidly decreasing amplitude in the inner layers. So the first star for which we could do something was, of course, the sun, and we could do a full inversion, a full scan of the internal rotation of the sun, and we got a bit of a, I would say, a surprise in the sense that you have latitudinal differential rotation in the convective envelope. The equator rotates about 30% faster than the poles. Note that when we talk about the poles, we can only go as high as 75 degrees in latitude in terms of what the inversion kernels can give us. And the second thing that is important about the solar rotation profile is solid body rotation in radius in the inner radiative layers, and a quick transition close to the base of the convective zone that is called the tachocline, where you have the degeneracy of this latitudinal differential rotation on one single rotation profile. Another important aspect of the solar profile is that we don't have access to information below 0.2 solar radii, because we only have acoustic oscillations detected so far, and they don't give us access to the core. So, of course, this was a bit of an issue when people started to comparing to, for example, rotating models, including the meridional circulation and the effect of shear instabilities, because they predicted a high degree of radial differential rotation inside a solar model, which was not observed. So you needed additional processes, additional mechanisms to rigidify the internal rotation of the sun. One such candidate was, for example, the large-scale fossil field. The first thing that you need to be able to do with the fossil field is to confine it, because you still need to be able to allow differential rotation in the envelope. And of course, you need also to avoid having this some sort of an issue of a dead zone in the region, in the radiative zone, where you can actually have some sort of a bump here in the inner layers that was already identified, if I remember correctly, by Rüdiger and Kichatinov in 1996. So you need some sort of an additional viscosity in the simulation to be able to have a fully rigid rotation profile when it is simulated. Another key candidate is magnetic instability, so the Taylor-Sproit dynamo, that reproduces nicely the observations if you do evolutionary computations. Again, there is a bit of a debate from the simulations. If you look at the paper by Zahn and collaborators, they seem to say that the Taylor-Sproit dynamo is not acting, but there is the question of the magnetic diffusivity in these simulations. And there is, I would say, some sort of a proof of concept that it works in favorable condition in the paper by Braithwaite and Sprout, where they can show that the dynamo is actually acting. So it's still a bit of a debate. And another candidate that has been proposed, I mean, the tests were made in the paper by Charbonnel and Talon also. They show that internal gravity waves generated by the Reynolds stress, the turbulence at the base of the convective envelope, can lead to, I would say, a slowdown of the internal regions of the sun. The problem comes again from simulations, is that, I mean, the simulations seem to say that you would have an oscillation, some sort of a wave front that will be frozen inside the rotation profile, and that would disagree with the observed data that is extremely flat. And there is no actual quantitative comparison in the paper by Charbonnel and Talon, so we cannot judge that also from evolutionary computations. A key problem in constraining the physical nature of the missing mechanism inside the sun is that we don't have access to the core. If you have a fossil field, you would, for example, predict a completely rigid rotation profile, whereas magnetic instabilities, for example, would predict a spin-up due to the stabilizing effect of the mean molecular weight gradients that are present in the region where thermonuclear reactions occur, so would have a spin-up of the rotation of the core. And for internal gravity waves, you could actually predict a slowdown of the rotation of the core, but we are blocked at 0.2 solar radii. And there were claimed detections of G modes already in 2007 and 2017 that would predict a spin-up, but they have been seriously disputed in the literature. So at the moment, we don't know. So that's, I would say, the current state of the issue. People could do similar work for other stars than the sun, but the data set is it's of a much lower quality. For the sun, we have more than 2,000 frequencies observed. For other stars, it's around 50. So you're not working with the same data set. You're not able to do a full scan. of the internal rotation of the stars, what you can do is having an average rotation in the radiative zone. And comparing these measurements to the surface rotation given by spots or by V sin I measurements, Ben Omar et al. In 2015 showed that it was consistent. I mean, the two measurements were consistent with each other, which went to this idea that main sequence stars rotate as solid bodies. The thing for the other stars and the sun, to be clear, and even for the sun, we don't know if there is a spin up or a slowdown in the core regions. We don't know if it's completely solid. Especially for these stars, we don't have the resolution to see exactly how the rotation profile behaves. It's more like a comparison of average that we can do here. For another thing that I would like to tell you also about these issues with angular momentum transport is that an inversion of the internal rotation is not the only trace that it would leave in observations. For example, since the evolutionary phases, especially the main sequence, is relatively long, any process that will counteract, for example, the effects of gravitational settling will have time to act during the main sequence. And for the solar case, that's something we can actually see. If you, for example, introduce the Taylor-Spark dynamo in an evolutionary computation, you're able to reproduce the internal rotation of the sun, at least the measurements we have, and you're able to actually reproduce the lithium abundance, the lithium destruction at the age of the sun. This is, for example, what you get with a standard model. You have no depletion as soon as you go on the main sequence. But if you have an additional, some sort of effects of rotation and a small shear coming from the counteraction between the differential rotation and the regulation by the Taylor-Spark instability, you have something that can reproduce the lithium, but also counteract enough gravitational settling so that low metallicity models actually reproduce the helium abundance in the convective zone. That is at least a part of the solution to what we call the solar modeling problem. So that's something that you have to keep in mind also with angular momentum, is that you can have traces also on chemical elements. As soon as the star evolves to later phases, the problem changes. The information you have access to is of much higher quality, I would say, because basically what happens is that the core is contracting, the Brun-Weiser frequency increases, so the characteristic oscillation of gravity modes increases. In the meantime, since the radius is expanding, the characteristic frequency of acoustic oscillations is decreasing. And then at some point, the two cavities can become coupled, and you will have what we call mixed modes. And mixed modes will be nice in the sense that they have a high amplitude at the surface. They will be easily detectable on bright stars also, because there will be subgiants and red giants, but also a high amplitude in the core. So they can give us access to the internal rotation of these stars, of distant stars. And internal, the inner 1% of really the core regions of these objects, which is not feasible even for the sun. And looking at this, thanks to the data coming from the Corot and Kepler satellites, we could see that differential rotation was actually present inside these stars. The core, for example, for the subgiants studied by Sébastien de Heuvers, is rotating faster than the envelope. If you look here, you have the core rotation as a function of, and the envelope rotation as a function of log g. You see the core is rotating significantly faster than the envelope. And we have similar results for red giants, for example, in the paper by Paul Beck in 2012. But the problem is that it's orders of magnitudes of difference between the observations and the predictions from the models, especially the models including only meridional circulation and the shear instability. Another key feature is that when you look at the core rotation as a function here of a proxy of the evolutionary stage, which is the density of mixed modes in the oscillation spectrum in the paper by Charlotte Géant, you can see that, there is no clear trend of a spin-up of the core of the red giants, what you would actually expect. So you have something in the paper of Moser 2012, they actually predicted even a spin down. In this case, it seems to be something more constant. And you have a similar trend for the clump stars. So that's something that is unpredicted by the models, and that is still a big issue in terms of understanding how an efficient angular momentum transport mechanism is acting in the radiative layers of these stars. So one work that has been done by Patrick Egenberger in Geneva is to look at some sort of constraints on the average efficiency of this missing angular momentum transport process. And to do so, you need to compute not only the core rotation, but the ratio of the core to surface rotation that you have for the subgiants. And you can then put, if you want, an additional viscosity in the angular momentum transport equation and calibrate the viscosity for each subgiant star. And then looking at which one is the more evolved, as it is classified, for example, here in this sequence, you can see that this additional viscosity is reducing when you look at older objects. So this means that the average efficiency of the process is decreasing on the subgiant branch. The problem is that it re-increases on the red giant branch. So there is some sort of I would say, difficult behavior to reproduce because you have something fading away on the subgiant branch and then a recoupling that appears on the red giant branch. So we don't know if that it's something like a second mechanism, something fading away and something taking over, or a change of regime in a physical process. So of course, facing this resurgence, I would say, of an issue that was already present in the solar models, you can test the candidates we have already at hand. And the issue is that the magnetic instabilities are not efficient enough to counteract, to produce this low degree of differential rotation that we see in subgiants and in red giants. Similarly, the internal gravity waves generated by the Reynolds stresses are unable to do the trick either. And the fossil fields, we'll see that they could be a solution, but we see that there are cases that do not respect the rotation laws predicted by large-scale fossil fields. This led people to consider revised prescriptions. For example, instead of considering internal gravity waves generated by Reynolds stresses, people looked at internal gravity waves generated by convective plumes, or modifications, I would say, to the magnetic instabilities or transport by the mixed modes themselves. This last process will be only efficient, I would say, above the red giant luminosity bump. So it's not going to be efficient for the subgiants and the red giants, the early red giant branch stars. The internal gravity waves generated by plumes, they have been shown to be okay in terms of timescales. They can counteract the contraction and reproduce the core rotation, I would say, of the subgiants. The big issue of these computations by Passon and collaborators is that they have not been implemented in evolutionary codes. So it's more like I would say, semi-analytical models that are patched to the evolutionary sequence. And we don't know about the impact it has on the main sequence. Again, we have no prediction of what would happen to a solar model, including these processes. The only thing that is clear is that it's not going to be efficient to reproduce the observations for the red giants, because then the mean molecular weight gradient barrier is too strong for the waves to be able to penetrate and extract angular momentum. So on the red giant branch, already on the early red giant branch, it's not going to be efficient enough. For the magnetic instabilities, well, there was a recent paper by Fuller and collaborators that showed this plot of an 1.6 solar mass star going through the core rotation of the RGB stars, the core rotation of the clump stars, and fitting also the rotation periods for the white dwarfs. The problem is that, so they said, okay, it seems to work with one single calibration of this free alpha parameter. The problem is that if you look at the details of the transition between the subgiant branch star and the red giants, at best, you're able to reproduce 2 out of 6 of the red giants, of the subgiants, and you're missing on the red giant star. That's the star studied by Maria Piadimoro, and these are the stars studied by Sébastien de Heuvel's. And if you wish to reproduce the red giants, you have, you don't have enough differential rotation on the subgiant branch. So again, this is this idea that there is something going on at the transition between the subgiant branch and the red giant branch stars. And a similar issue is actually happening for the secondary clump stars and the white dwarfs. And again, the alpha parameter needs again to be recalibrated. So it's not a unique value of the parameter and a unique solution that is provided here by Jim Fuller. The other thing that has been recently put forward are large-scale axisymmetric fields that have been very recently consistently implemented in stellar evolutionary computations. And you have to commend on the effort that has been made, because these are very, very difficult computations. And it's Takahashi and Langer in 2020 that showed that they could actually reproduce the contrast of rotation for the subgiants and the co-rotations of the red giant branch stars simultaneously. And the main features of this rotation profile is a rigid body rotation in the radiative zone, and then a power law dependence to the power minus alpha in convective regions. That was also found in Kissin and Thompson 2015. And the issue again is when you look into the details of these astroseismic constraints. For example, for Kepler 56, there was a paper by Klein and Quattert in 2017 that said, okay, we can reproduce the splittings, the rotational splittings with this type of profile. But if you do a really dedicated modeling to this star and you keep alpha in between 1 and 1.5, you're not able to actually reproduce the data. So that's what I show you here. You have the rotational splittings as a function of frequency. And you see, so these are I would say the G-dominated mixed modes. So the mixed modes that have a high amplitude, a very high amplitude in the core. And these are the pressure-dominated mixed modes that will have a higher amplitude at the surface. And if you keep a power law with an alpha limited between 1 and 1.5, you get the orange dot. So you get something that is able to reproduce the core rotation. That's I would say not easy to do, but that's feasible. But you're missing out on these P-dominated mixed modes that are giving you the contrast, if you want, between the very deep core and the upper regions, if you want, the rotation in the upper layers of the star. So looking at the values of alpha that would be needed to reproduce the data, you get an alpha that is at about 3.9. And you get a very slow rotation also at the surface. So this solution seems to favor a transition that is located in the radiative zone, and especially close to the hydrogen burning shell. So close to regions where you have large mean molecular weight gradients that are acting. And these type of profiles, the blue and the orange profile here, can actually very well reproduce the data. You see here the position of the hydrogen burning shell in the Brunt-Väisälä frequency of this dedicated model of Kepler-56. So that's also, I would say, something that has to be, to be emphasized, is that for these astroseismic data, you need to be extremely quantitative. When you look really at the behavior of the models, each time you need to have I would say, a dedicated model optimized to reproduce the observations, at least also from a structural point of view, because otherwise the properties of the mixed modes are not going to be perfectly reproduced. So what we know, I would say, is that we're missing something in the models, and this astroseismology and helioseismology are showing that an efficient mechanism is acting. And I would say there are few candidates. The problem is that none of them are working perfectly at the moment. We are missing on the behavior of the efficiency, and we're missing some efficiency for the angular momentum transport. And of course, also the link with the chemical gradients, because if you have sometimes regions where it's the thermal contribution that dominates, or the mean molecular weight gradient that dominates. But in regions like the hydrogen burning shell, both will contribute significantly, or at the base of the solar convective zone also. And these are difficult regions to take into account to model using, efficient angular momentum transport processes. What we could hope for is a measurement of the solar G modes, and also a better location, I would say, of the transition in the rotational profile in subgiants and red giant stars, and a better characterization of whether it is extremely sharp or smooth. And from there, we would gain a recipe that would be anchored in seismology, that would use the data we have in seismology, and we could try to extrapolate it to more massive regime, keeping in mind that this will only be still an extrapolation. Thank you very much for your attention. That was it.
Thank you very much, Gael, for this very dense talk. We have just time for maybe one question. We want to keep the time schedule. For a rapid one, if somebody, yes, please. I see Norbert, please. Norbert.
Yeah, thanks for a very interesting talk. I had a bit of information overflow, so I might not have grasped everything correctly, but I was wondering about the data side at the red giants. In one or two plots, you showed just one star there. And I was, I'm a bit biased from the massive star side, and the massive star side is all about binaries. And if you just have one red giant and you calibrate your method with one red giant, you may have bad luck, and this guy has perhaps merged with a companion or has done other funny things.
So on that aspect, I would say that's true, that having only one data point is a bit of an, I would say, of an issue. But we're showing here the star studied by Maria-Pierre Di Moro, but Kepler-56, for example, would be at the same region in this plot. And you have also, I think, stars studied by Santiago Triana, if I remember correctly, and a similar issue is appearing. The big problem for the calibration of the efficiency of the transport in red giants is that we need core and surface measurements. And if you take, for example, a measurement from the star spots that we have some spots for red giants, we seem to be biased towards also faster rotator that could have undergone some sort of interaction. So for that, we need, from the seismology point of view, dipolar and quadrupolar modes. That's what will at least a very good depiction of the dipolar modes as we had for Kepler-56. There are a few stars for which we can do the job, but nevertheless, this issue will stay. I would say for Kepler-56 and for the star for Maria-Pierre Di Moro, it means that there is something else. It's not a simple, I would say, a simple solution there. They are difficult to reproduce. On that, I agree. But they are, in a way, representative in terms of core rotation, also of the rest of the sample from Charlotte also.
Thank you, Gael. Thank you for your answer. I think that now we can go to the second talk of this session by Sébastien Salmon, who will speak about asteroseismology of beta Cephei stars.
Yes. Okay, so can you see my screen?
Yes.
Yes, we see.
So great. So first I want to thank George for having organizing this session, and I'm very pleased to be able to present you today this talk on beta Cephei stars. We'll just start showing you this diagram. So you see all the pulsating stars on the main sequence. You see that we have different groups. So today I will concentrate on the most massive of them, the beta Cephei stars. But I want also to bring your attention to intermediate mass stars showing pulsation, which are the SPB stars and the gamma dwarf stars. If I have sometimes at the end of the talk, I will show you also that they are very interesting targets for characterizing the internal rotation with Astro Seismology. But today, as I said, I will focus on beta Cephei stars. So typically, they are between 8 and 20 solar masses, and they present period of pulsation between 2 and 8 hours. So why are they interesting? Because if you look at the structure, it's rather simple. You have the convective core surrounded by the radiative envelope. And as the core recedes during the main sequence, you have a chemical composition gradient that appears at the boundary of the convective core. And that gradient is very interesting because he bears all the signature of the different physical process you can have in the star. For instance, if you consider overshooting, you will have a shift of the location of the gradient. If you consider mixing induced by rotation, you will have some kind of diffusive mixing, and that in that case, the gradient will be smooth. And all those features that are imprinted on the gradient can be constrained by the Astro Seismology. And in this slide, I give, you see there are many prescriptions that have been proposed for overshooting. So I will show you if we can test those different prescriptions with beta Cephei stars. There is also the question of the transport processes, of angular momentum, magnetohydrodynamic instabilities. And I will also show you that we can have some hint on this process. No. A brief introduction to star pulsation that was already given by Gail, but I show you here small animation of those pulsation, just to indicate that typically we use 3 numbers to characterize a mode of pulsation in the stars, which are the radial order, the angular degree, and the azimuthal order, which are all related to the nodes of the oscillation. And as you see, depending on the geometry of the mode, we have a deformation of the star which is different. So by studying them with photometry or spectroscopy, we can identify the mode. And we can also, of course, obtain the frequency of the modes. And these information are very precious because the modes, depending on their nature, on their geometry, they probe different layers. So for instance, I give you a very simplified oscillation equation for stars. And you see 2 very well-known frequencies, the Brun-Wasser frequency and the Lamb frequency. And that equation has 2 oscillatory solutions. And if you look at this solution in a typical beta Cephei model, where I give the Brun-Wasser frequency in the solid line and the Lamb frequency in the dashed line, the first series of solution will be the modes that can propagate in the deep layer of the stars. You see with the blue line. I'm sorry, normally it should have more text, but well, those modes are gravity modes. So typically gravity modes probe the deeper layer of a beta Cephei star. The other type of solution you will find are the pressure modes, which probe the superficial radiative layers, and very common in beta Cephei stars, the mixed mode. You see, in some parts, you have a very small evanescent region between the cavity of propagation of the gravity mode and of the pressure modes. And so you can have a coupling between the gravity and pressure modes, which are known as mixed modes. And they are very interesting because they give you a very important information on the gradient of chemical composition. Now we can have a look at the effect of rotation of star pulsation. First, a look at the direct effect of rotation on the star structure. It was shown in a series of papers by Miglio et collaborator, Montalban and collaborator, and Mario Goupil in Paris, that the effect of rotation imprint, of course, an effect on the structure. If you look to the left, you have the evolutionary track of a model without rotation and a prescription for overshooting of instantaneous mixing in solid black line, and calibrated to that track a Geneva model with rotation in dot line. And if you look to the right at the chemical composition profile, so the hydrogen abundance, you see of course, the size of the convective core, which is similar in the point of comparison. But you see that the model with rotation is moving the chemical composition gradient, which the model without rotation don't have. And that difference in the structure has an impact on the frequencies. If you take a typical beta Cepheid model, you see here the evolution of the frequency of mode with different radial orders as a function of the effective temperature. And if you look at one particular series of dots, you see in gray the model with rotation and in black the model without rotation. And you see a shift in the frequency that appears. I highlighted two regions in pink, where you see clearly a distinction in the frequency of the model in gray and the model in black. And these are a mixed mode actually. And the shift in the frequency is large because it is very much larger than the typical precision we have on the observed frequencies in beta Cepheid star. So in principle, with the asteroseismic modeling, we are sensitive to the mixing at the boundary of the convective core. Now there is the direct effect of the rotation on the frequencies of the mode. So with rotation, there is a lift of the degeneracy on the azimuthal order. And so we have the frequency of the azimuthal mode, which is different of that of the Axisymetric mode. And that shift in the frequency can be treated in relatively slow rotators with a perturbative treatment at first order that give you a direct link of the frequency of the azimuthal mode with the kernel, which is given in the integral, and the profile of the rotation inside the stars. And those kernel, once you have done the modeling of beta Cepheid stars, they are fixed by the structure because those kernel are a function of the eigenfunction of the modes. So if you have the kernels, then you can make a kind of small inversion of this relation and get the internal rotational profile. The approach is robust. For instance, you have here in the top panel the Braun-Vassal frequency for a model with rotation and a model without rotation in black, solid line. And you see that if you are able to have a good modeling, a good star model representing the frequency you observed, the kernel won't be very different between the model with rotation and the model without rotation. Yeah. So you see that the kernels, for instance, given in the bottom panel, are very similar, and important also they give you, depending of the mode, and information on the layers close to the convective cores. You see that the kernels in the bottom panel, given by the black lines, have the amplitude very high in the region between 0.1 and 0.2 of the normalized radius. You can also include higher order terms in the perturbative approach to compute the frequencies of the azimuthal mode. Those higher order account actually for centrifugal effects, and they lead to asymmetry in the rotational splitting. And that asymmetry is also in some beta Cepheid stars they are observed, and so they give you an information on the distortion of the star. Now, here is a table that gives you the most well constrained beta Cepheid stars at the moment in the literature. So you can see first that for all those stars, there is a rather good determination of the overshooting parameter. So that means that we are really sensitive to the extent of the mixed region at the core of the stars. However, you cannot make a general rule or general tendency from those results because it's somehow dependent of the formalism you use in the models for the overshooting. You can have an evolutionary stage effect. All those pulsators are not in the same stage on the main sequence. So if you want to have a good comparison, it would be optimal to make again a new asteroseismic modeling of all these stars with the same star models and with the same asteroseismic methods. So for the moment, this is something that hasn't been done. But also what you can see is that there are 4 beta Cephei in which we have a ratio of the curve to surface rotation. Actually, in these 4 stars, we have the observation in the frequency spectra of rotational splittings. And you see that for 3 of them, the expected curve to surface rotation are between 2 to 6. We can go a bit further with the help of the rotational splitting and in investigating in more detail the internal rotation law. So this was done for the Nueri beta Cephei stars by Suarez and collaborator. What they do was testing 2 extreme scenarios. One is rigid rotation on the evolution of main sequence, and the other was local angular momentum conservation. And they show clearly that the rigid profile was rejected. You see here, it's the evolution of the model for Nueri of the theoretical rotational splitting in black and dashed line. For UR means the uniform rotation and SR the cellular rotation. And in the gray box, you see the effective temperature, which is expected for Nueri. You see that the reproduction of the observed splitting, which are given by the horizontal lines, it's only possible to explain both the G1 mode splitting and the P1 mode splitting when there is cellular rotation. The uniform rotation, so is clearly rejected. And you saw also that there is another splitting, the P21, which is not explained by any of these rotation law. And this is still a mystery, but there is good in that there might be a misidentification of the degree and of the azimuthal order of that mode. No, there is V stars, HD 129929. So it was observed in 2004. It's actually the first beta Cephei star in which the differential rotation was deduced with help of 2 rotational splitting, one of the G1 mode and one of the P1 mode. And the result I will show you now are a fresh result we did with collaborators in Geneva. And we did something similar. We test different law and see if we can have a glimpse on the evolution of rotation during the main sequence for that star. So we use the parameters that were derived in the Astro Seismic modeling by Dupré and collaborator. So I show you here the rotational kernel to the left of the P1 and G1 mode for the model of this star. And you see that the G1 mode is clearly more sensitive to the central layers close to the convective core than the P1 mode. So you have 2 rotational splittings. If you assume a linear law for the rotation, you can deduce, of course, the parameters of this law, and you see what was done by Dupré and collaborator. He found the law that you find, you can see on the right. Now, what we want to do now in Geneva is that it's to exploit the fact that the star is a very slow rotator. So that means the meridional circulation is not very efficient, and that we can try, for instance, to retrieve what was the profile of rotation on the ZAMs. So what we did was assuming local angular momentum conservation, starting with the profile on the ZAMs. In this case, we test a rigid profile, which is given by the black line in this plot of the normalized rotation. And you see, we evolve the model to get to the model of HD, of the HD star, and we get the profile in blue. And that profile in blue clearly is not able to reproduce the splitting that are observed in the stars. We give the linear law, and we see that clearly we don't have the same tendency with the blue curves. Next, what we did was testing a linear decrease on the ZAMs of the rotational law in black still. And you see that it then evolves to the blue profiles, and the blue profiles is actually performing well at reproducing the observed splitting. We see that it could be expected because it is very similar to the trend given by the green line. And so we have a constraint on the ZAMs. We see that on the ZAMs, the curve to surface rotation was about a factor 2. So what is ongoing now is that we want to try testing the law of accretion on the PMS. You have, for instance, an example of a rotational profile on the ZAMs for model with accretion in black and with the meridional circulation, sorry, that was cut off. So we are certainly in a similar case because it's a slow rotator. So we are now trying to test a profile with law that are given in gray to see if they can, with the evolution, reproduce the splitting and see if we can get constraint on the equation. Another test we can do is trying different transport process also for these stars. So you can see here test of magnetic instabilities. To the left, you see it was the Fuller mechanism, the Fuller prescription that was implemented. You see the evolution of the rotational profile for a star representing HD. And at the edge of HD, so the light blue line, you see that we have almost a rigid profile, so which cannot reproduce the observation. There is too much coupling between the core and the envelope. We also test the classical Tyler-Sprout instability, the original prescription, I would say. And you see to the right that then we have a more important contrast between core and surface, but still you see the value. We should be between 3.6 and 4, and we are clearly under that. So we cannot reproduce the observational splitting as well with that model. So as a conclusion, with the beta CFA, we can have a good constraint on the extent of the convective core, but we have to be careful that it can depend on the prescription in the models and also on the metallicity, so on the chemical mixture you adopt for the modeling. And you need to have a tailor-made method for analysis of that extent. And the ideal would be to redo all the beta CFA with a same method. Extra mixing process in principle leave also a signature on the frequencies, but there's not been yet successfully applied in beta CFA modeling. And we see that they are really good target for characterizing the internal rotation, but also the past history of that rotation. Still, we have to be careful because the two stars I presented are slow rotators, so it's not easy to extend this to a general rule. And now if I have some time, I have just another slide to briefly give you some references to results which are very promising for characterizing internal rotation on the main sequence. It's namely the result we get with the Kepler mission on gamma Dor pulsators. So they are very interesting because now we have hundreds of gamma Dor that have been observed in Kepler where we detect what is known as the G-mode period spacing. And what is interesting is that the spacing between the periods of gravity modes in those stars is known to follow a linear trend when there is rotation, and the linear law will give you actually the value of the rotation, the mean value of the rotation in the cavity of propagation of the G modes. And so in hundreds of modes, now we have that value of the rotation. So it's a first important step. If we can have, by other means, the surface rotation, then we will be able to detect the law. And also, if we can have the core rotation, which is not accessible directly with the gravity mode, then we have a complete profile. And that's where it's interesting, because with the Kepler mission, we also detect Rossby and inertial modes. The Rossby modes are interesting because they are more located at the surface, so they give you a hint at the surface rotation, while the inertial modes are really giving you a direct constraint on the convective core. And so in Sayo, in a paper by Sayo and collaborators, very recent, they found inertial mode in 16 stars, and they were able to give a ratio of the core to envelope of the rotation, which in that case appeared to be compatible with rigid rotation or close to rigid. Yeah, for gamma Dor, we have also some of these stars where we find classical splitting of pressure and gravity modes. And in one star, then it was possible to have an inference on the core rotation, and the ratio in that case was about 6, so more in line with result from beta CFA stars. And still with the Kepler mission, we have also, but to a lower extent, results for SPB stars. So SPB stars, there are about 5 solar masses. They have the same structure as beta CFA stars. And there is a dozen of stars in which gravity mode period spacing were detected. So we have also the internal rotation of the gravity mode cavity. But we have also another feature in the gravity mode period spacing. It can also present an oscillation, and that oscillation gives you the information if the chemical composition gradient is rather smooth or sharp. And it seems from result by Peterson from this year that in most of the SPB star of the sample, there were a mixing of diffusive nature at the boundary of the convective curve. And that's all.
Thank you, Sébastien. Thank you very much. So there is maybe just time for a very quick question. If somebody wants to raise her or his hand. If not, maybe I have just a question about the gamma door, the one which presents a high contrast. Is it also a slow rotators?
Yeah, actually, the surface rotation is rather slow. Yeah.
Okay. So thank you very much, Sébastien. So I have now, I will give the floor to Norbert for the third talk, who will speak about rotation in massive stars. You have your mic, which is not open. Oh.
I do things in the wrong order, it seems. I have to first mute and then share my screen. Okay. All right.
Okay.
I would like to start with thanking you, George, to have me here. It's a very nice opportunity to show a few ideas, and we are a small crowd, but of important people, so I enjoy the task and hope you will enjoy the talk. So I just will discuss essentially one take-home message about the rotation of massive stars. And just starting out, I would like to show you a diagram which I stole from ICRANet, from the Royal Belgium Observatory, showing you the average rotation rate of main sequence stars as function of spectral time. You see that, as we heard about in the previous talks, also the low mass stars all rotate very slowly, while the upper main sequence stars rotate much more rapidly. And the upper main sequence stars are what I would like to discuss here, where it gets a bit more complicated towards the O stars, which I leave out for the moment. So if we just look at the observational evidence, how fast are these stars rotating? Let's look at the dwarf stars. Here, the early B dwarf stars. This is from the the Flames Tarantula survey. 300 O stars roughly are in here with high quality spectra. And what you see is that the distribution of rotational velocity is at least bimodal. So there is a group of slow rotators, which contains about 20 or 30% of all the stars, and then a group of faster rotators. And then I would claim here is also, you see a tail of very fast rotating stars. Actually, there would be more here if BE stars were included in this sample, which they are not. We can look at the A stars as well. This is from a paper by Zorek and Royer from 2012. And just let's look at the upper part of this diagram. So stars more massive than 2 solar masses or so. You see the probability density of finding a star at a certain rotation density color-coded here. And what you see is that in this regime here, it's also a bimodal distribution. You have slow rotators here, then you have a gap, and then you have fast rotators. And then I would claim again, you would have a tail of even more rapidly rotating stars here. It's a high rotation end. Now, what we see this behavior even more clearly, I think, from the recent HST photometry of young star clusters in the Magellanic Clouds. I have overflow information here on this view graph. Sorry for that. It's 4 clusters, just to show you that this is a very generic picture coming from this data. So let's discuss here this cluster NGC 1755 in the LMC. What you see is there is So at the turn of mass, roughly the turn of masses of these clusters are of the order of 5 solar masses, 7 solar masses, something like that. There is a very sharp main sequence which contains most of the stars, actually 60% or so. But then you see there is a so-called blue main sequence beneath it, which is clearly separated. You can see there's a gap in between. And you see this in all the clusters. Furthermore, you see most clearly here in NG3330, there is another separate sequence of stars here. These guys, which are colored in red, are emission line stars. So that's most likely all BE stars. So that's 3 groups of stars, which we found also in the previous diagrams. If we interpret this in terms of rotation, I should say to focus here, that's too fast, on one of these clusters. These guys here are also interesting, but that's just visual binaries where you have 2 stars in 1 pixel. Most of them are probably physical binaries. I don't want to discuss them here, but you can ask questions about them if you're interested in that. But the interpretation of these blue and red main sequence is that there is a difference in the rotation rate of both groups of stars. And that can be seen if we compare this with rotating stellar models. You see here the colored lines are isochrones for stars of different rotation rates. So this parameter W gives you the rotation rate of the star initially as function of its critical rotation rate. Sorry, not as function, but divided by the critical rotation rate. And so this slow rotation, this parameter doesn't matter very much, but because it's a quadratic effect, it's rotational velocity. But then once rotation becomes of the order of 30–40% of critical, you see that the color depends quite a bit on how fast these stars are rotating. And one can very well reproduce the blue and the red main sequence bands by stellar models which rotate slowly and roughly half critical, like we have seen in the spectroscopically obtained distribution of rotational velocities for B stars and A stars. So it's a very coherent picture which we get from all these observations, namely that we have 3 groups of stars which rotate with different velocity. Most of the stars perhaps with roughly 50%. Then there is a group of stars which rotates slower. We can't really say exactly how slow, but 20% would reproduce all the data which we've seen so far. And then, sorry, that's group C. And then there's a group of stars which rotate very fast. That's emission line stars. And you can even see in these star clusters how these groups come about as function of evolution, because as we go down from the turnoff in magnitude, we go to more and more unevolved parts of stellar evolution. So these guys here are actually completely unevolved. And what you can see from that is that the slowly rotating group here must come out very, very early in the evolution. And the emission line stars, they go down maybe 2 magnitudes below the turnoff, and then they stop. Yeah, so that tells you what evolution does. And so the interpretation of these kinds of effects we can do with stellar models, of course. One is to look at single star evolution models. Now, if you look at single star evolution models, here prod models analyzed by Ben Hastings in Bonn, you can find similar analysis in the paper of Sylvia Ekström. When we look at the time axis here and say a star is starting with 50% of critical rotation, then what you see as a star ages, its ratio of rotation to critical rotation increases. That's the color coding here. The closer to black it goes, the closer the stars are to critical rotation. And so you see these single stars which start out with 50% of critical rotation, they can reach 60, maybe 70%. It's very hard for them to go very much higher, independent at which mass or metallicity you're actually looking. So what we do is we also analyze this issue with detailed binary evolution models using the MESA code. Well, this is just a summary of all the physics we put in there. It includes, of course, differential rotation and rotational mixing, but also tidal spin up or tidal or spin orbit coupling, and also magnetic angular momentum transport. But it, of course, also includes Rauschenlob overflow and spin up of stars by accretion. And so we interpret our results then in the Hertzsprung-Russell diagram. I have a small animation here showing you the evolution of a star cluster in the Hertzsprung-Russell diagram. So that's the initial situation where all stars are born here on a rather boring zero-age main sequence. And then what evolution does is, as function of times when stars expand, binary effects can turn in, and you get two types of binary effects. You get stars which merge, which turn out to be often very slow rotators to the left side of the zero-age main sequence. And then you get the accretion stars, which are rapidly rotating, which are these stars here to the right side. And so the color coding gives you the current rotation rate of all these stars. And what you see, if we perhaps stop this and go to a time more comparable to the clusters we've seen, we retrieve this split of main sequence. We have the unaffected stars still in the middle. We have then the very rapid rotators, which are redder, and we have the slow rotators, which are perhaps merger stars to the other side. And so our working hypothesis here is that we have these three components, and that all these components, well, that the main component is just how stars are born in general, and that the other two components are actually occurring from binary effects. Now that the component B, which is the rapid rotators, comes from accretion, is more and more underpinned by observations. The idea is rather old. Already Packard in '89 showed that only 5% of mass accretion can spin up a star very much. And Van Hastings showed now that binaries can produce up to 30% of a population as BE stars. There's evidence that in binary systems, there is basically, or in main sequence binary systems, there is basically no BE stars found, which means that they are probably of binary origin. And also how far down the cluster, from the cluster turnoff we see them, points that really most BE stars are formed from the binary effect, because single stars can only produce BE stars very close to the turnoff. Now these BE stars, this component B, is very interesting because the prediction would be many of them have actually compact companions. And in a paper last year, we showed that, for example, as function of the mass of the main sequence star, the probability to find a black hole next to it is of the order of a few percent. Here in the B star regime, it's maybe 2%. In the O star regime, it gets even higher. And you can say that's a low probability to find a companion. But then if we look at the fraction of the OB plus black hole binaries where the O or B star is rotating very rapidly, then it's very high. You see the distribution of rotational velocities of these systems is such that in the logarithmic scale here, most of the systems rotate very, very rapidly. And so if you are interested in finding black holes in binary systems, you should look at the BE stars. That's the message. So I'll skip this one. Let's look at the slow rotators. So where would the slow rotators come from? And The idea which we follow here comes from star formation theory, because recent models of binary formation predict that because in binary formation, the birth cloud is still there in the early evolutionary phase of the binary evolution, and the tidal effect will lead to drastic orbit decays. And the prediction is that 30% of all the binaries actually merge during the pre-main sequence or early on during the main sequence evolution. Now that fits to the 30% of stars being slow rotators, for example, amongst the early B stars, and it matches very well to the blue main sequence stars in the star clusters, which we've seen. Now, why would mergers rotate very slowly? Well, Fabian Schneider and co-workers have just shown in a multi-D simulation that actually a merger product evolves such that when the binary system merges, the star puffs up to a giant structure and then loses a lot of mass in an equatorial wind, which slows down the star such that the merger product, when it settles on the main sequence again, is very slowly rotating. So the color coding here again is rotation, and blue means it's very slow rotation. So you expect actually merger products to be very slowly rotating stars. You expect 30% of the binaries to merge. So I think that's together a very good explanation for the group C, which we have. There's also other observational evidence that this orbit decay happens. This is from Ramirez Tanos et al. 2020. Last year, they measured the velocity dispersion in star clusters, young star clusters, as function of the age of the star cluster. And they see a drastic increase in the radial velocity dispersion of these clusters, which when interpreted as binary motion means that on average, the orbits decay drastically, and the binary radial velocity signal is drastically increasing over the first million years of the star, of the life of the star cluster. So my summary, very simple. Perhaps all stars are born, all the upper main sequence stars are born with the same rotation rate. And then there is two effects which lead to rapid rotating stars, namely mass accretion, and to slowly rotating stars, namely stellar mergers. And of course, in the slow rotators, we know there is the magnetic stars. Also in the simulation of Fabian Schneider, there's magnetic field created in the merger process, so that fits into the picture. And so if this picture was true, then we should be careful which stars we're analyzing. We've just heard in the previous talk, the beta Cephei stars that analyzed for pulsations were all very slow rotators. So maybe they are in this group C, and we could not readily learn something about the average massive star from such investigations. Thank you. I stop here. Take your questions.
Thank you very much, Norbert. Which is now, the talk is open for discussion, for questions. So please, if you want to ask a question, or open your mic. But if there is no question, I will ask one anyway. Okay, maybe I will begin. So at a given point, Norbert, when we look at the very fast rotating stars, the tail, it was supposed that they were coming from merging because they were fast rotating. Mm-hmm. Now it seems that it's a bit a change of paradigm. It is a slow rotating one which comes from merging. But my question is, where does this very fast rotating tail come from then?
Well, I agree that this is a change of thought. Earlier we have thought that, well, the fast rotators would come from binary interaction. I mean, we always knew that the spin-up process is leading to fast rotators. We understand the BE X-ray binaries in no other way, for example. But also for the mergers, yes, the problem there is that there is a lot of angular momentum in the system. Yeah, and so your first idea would be that the merger product is rapidly rotating. And many people, including myself, probably have said that a lot of times in the past. Now we have the merger simulations, and we need more of them. Fabian Schneider's simulation is perhaps not the last word, but you know, the idea is kind of convincing that you get a puffed up star from the merger, because there's also a lot of energy, of course, released in the merger process, the potential energy. And when the star is puffed up, it may have a strong wind and lose angular momentum very efficiently. We have to see whether this is true for, you know, low mass stars the same or not, and so on. So there's a lot of uncertainty in this. It just opens a nice way to understand all the different indications of, you know, how unevolved stars are actually rotating.
Okay, yes. Okay, thanks for your answer. We have still time for one question if somebody wants to ask. Maybe just since I have maybe a second one, which is probably not so pertinent to some extent, but of course, when we look at clusters, it may be that there is also some duration of the star formation in a cluster. It's not just one starburst, instantaneous. So it may have an impact, but of course, I agree with you that it would be strange that the effect that we see are due, for instance, to two bursts, because it seems to be very similar in every cluster that we see.
Yes, and also the point is that the distance here between these two main sequences is rather constant for a long time, yeah, for a long stretch. And if you have two different isochrones, you know, they would merge if you go to unevolved stars. So this feature you can never obtain with two bursts of star formation, and people understand that. That's discussed in the literature. It was the first idea, in fact, which people have discussed.
Okay. So thank you very much, Norbert. If there is no other question, I think I thank you for your talk, and I will give now the floor to Volker Brom, who will speak about rotation of propulsion-free stars.
Okay, good morning to some of us. I believe good afternoon to most of you.
Yes.
Just to start, let me echo what Norbert said. Thanks to Georges for organizing this, and also what Norbert said. It's clear that we have a small group, but it's also clear that a significant fraction of the world's expertise in stellar astrophysics evolution is in our virtual room. So it's a real pleasure to be here. So Georges has given me the task to push our discussion of rotation, stellar rotation, to the limit, and this gets us to the topic of rotation of the first stars, population 3 stars. And in terms of big picture, just to put this into context, astronomy, cosmology over the last century has worked very hard to reconstruct the entire history of the universe. And of course, by now we have in direct view over 90% of the history of the universe. But there is a final frontier, if you like, of cosmology, and this gets us into the first billion years of cosmic history, when structure formation starts, galaxy formation starts, star formation begins, and right when we contemplate this final piece in our cosmic worldview, so to speak, then we now, because of the cosmic microwave background, we know the initial conditions extremely well, and so it really makes sense to predict the onset of star formation, the end of the cosmic dark ages. And of course, the idea is that we are also at the verge of pushing this observational frontier further back towards the Big Bang with all the frontier telescopes, observational facilities that are about to come online. And of course, with a bit of luck, in a few months, we will see the launch of the James Webb Space Telescope. So let's briefly summarize some of the the elements of what we know about the beginning of star formation, the first stars. So there's what we could call, with a grain of salt, the standard model of population 3-star formation, because one of the appealing features of this aspect of star formation at the very early universe is that in principle we have all the ingredients in hand, and they are really very fundamental. On the one side we have lambda cold dark matter cosmology telling us about structure formation in the universe. We know the cosmic dynamics, the matter energy content of the universe, and crucially we also have a very good understanding of the initial density perturbations calibrated by the CMB. And then the second part is we combine this with the chemistry and cooling properties of primordial gas, pure hydrogen, helium. So really a very, very simple baryonic ingredients. And then if we combine them over the last decade or two, we have developed a basic picture of how star formation got going in the universe. And some elements of this emerging framework have proven very robust. Basically all numerical groups, different methodologies agree on some aspects. And what we all agree on is that if we consider the cosmic web, the cosmological initial condition, large-scale environment, then we with these two basic ingredients, cold dark matter and primordial hydrogen helium gas, the prediction is that the first stars form in dark matter mini halos, few million solar masses, redshift 20 to 30 or so. And then if we have primordial gas cooling falling into these dark matter halos, then we get to a scale where for the first time in cosmic history, the baryons decouple from the dark matter masses of about 1,000 solar masses, the sizes of a parsec or so. So this would be the equivalent of what we would call in standard star formation theory a pre-stellar core. So this is a very robust picture of early structure formation. It's very difficult to change this. You have to do something rather drastic to the ingredients. You, for example, have to play with the properties of dark matter. But this is really a robust prediction of the theory. And then where we very much are at the frontier and where we very much are not yet fully converged and we don't have a robust final answer is then what happens to the formation of individual stars inside these host systems. What is the final distribution of masses? What is the primordial IMF? There's lots of work, ongoing work, and this has gotten quite involved, multi-physics, multi-scale cosmological initial conditions. And then one important frontier is if you have a primordial protostar, POP3 protostar forming in the center of a mini halo here in the center of this box, then at some point when masses grow to about 10 solar masses or so, then we get into the regime of vigorous radiative feedback. At some point, the feedback, the radiation pressure will push back on the accretion and will shut off accretion and will set a limit to the masses. As I said, this is not really converged, but there is first order or zero order, if you like, agreement amongst all groups, all simulations that have looked into this problem of the first star formation. They all agree that in the end we have an initial mass function that is top heavy to a considerable degree, with typical masses of a few tens of solar masses. So the typical outcome is progenitor masses for core collapse. There's also agreement that there is a range of masses extending to lower masses, higher masses. What the exact form or shape is, there's no convergence, no agreement, and we never really, just from pure first principle ab initio theory, we may not be able to really nail the exact functional form. But again, we have the first order agreement, and then an important test of this picture is how low in mass do we get? How can we constrain this from observations? And of course, at some point the question is, are there low mass survivors from POP3? This is an interesting target for stellar archaeology. On the other hand, we also want to push and see how high in mass can we get. And then one important tracer of this in principle is famous appearance stability supernova, which of course is theoretically posited. We have never with complete confidence seen any, but the idea is that the early universe should have produced them. So most of the work on first star formation has really focused on the mass spectrum, the IMF, and of course, that being said, with population 3, we are dealing with an unknown stellar population. And of course, it is very different from all other stellar populations, population 1, 2, where of course we have huge amount of empirical knowledge to guide theory. And of course, many of those this empirical base has been summarized by earlier speakers. There's this beautiful data to constrain theory. For the first stars, we don't have that. We have very little constraints. So we are really dealing with an unknown population. And then it's clear that we also need to address, next to the IMF, other aspects. What about the binarity, the multiplicity? I will not talk about this in this talk, but of course, our subject here is we want to focus on rotation. So there is developed quite a bit of very sophisticated work from the stellar evolution and nucleosynthesis community. And again, there are a number of key players in the room today who have pushed this. So there's a lot of understanding of how metal-free massive stars should evolve if we take rotation into account. But from the star formation viewpoint, and star formation in the early universe always means, as we have seen, that we have to take into account cosmological initial conditions. This is a very, very underexplored aspect. So what we know is limited. But just to mention, in an earlier, this I think was the first exploration of rotation in POP3 stars, where Athena Stacy looked at the cosmological simulations, and we were really tracking the buildup of angular momentum in a primordial protostar. And then, with some simplifying assumptions, we traced the buildup of the rotational velocity versus time, and this would be speed on the surface on the equator. And let's just focus on the solid lines. So the black line shows the actually predicted rotation, and then the green line would be the breakup limit. And the basic picture is a bit similar to what Norbert mentioned for massive stars in the present day universe, that at some point, especially when we settle the star on the main sequence during Kelvin-Helmholtz contraction, we reach the significant fraction of the breakup speed. There are a number of caveats, numerical uncertainties here, but let's not worry about this now. And then just to make one point in terms of overall angular momentum content in the protostellar environment. Then we have our prediction of how much angular momentum we have, and then we compare this with thresholds for things like chemically homogeneous mixing, what do we need in terms of angular momentum for GRB collapsars? And you see that there's uncertainty, but in principle there's lots of angular momentum content, and in particular, we should be able to have enough rotation to create a collapsar. This then gets us into the interesting aspect of gamma rebirths in the early universe. POP3 stars in principle should be able to produce gamma rebirths, there was this naive expectation that the Swift satellite would find them at a large rate. This has not been borne out. Swift has only found very few very high redshift bursts, but the message from cosmological simulations is that basically this is just sort of look at the red curve and the blue curve. These are sort of the kind of GRB rates that we would expect from the early universe, redshifts 10 and higher. And in principle, there are even with very conservative assumptions, there should be a number of high redshift bursts per year. So this high redshift GRB window is still largely untapped, and there are mission concepts, mission studies, like physoids, which in principle really would be able to hunt down the high redshift GRBs. So this is a window that is there that we should not forget about, and there is in principle a huge potential. So what I have said so far, this initial prediction, the first stars are all rapidly rotating, assumes there's no MHD, magnetohydrodynamics, in the picture. These are all simulations that are purely hydrodynamical. So in an exploratory study with Shingo Hirano, we looked at in a simplified way what might happen if we have magnetic MHD transport effects, and this is right in the primordial disk, and again, sort of this is very, very complicated, complex, but just to first order, what we found is that there is an indication that in the end there may be a bifurcation in terms of rotation, surface rotation versus time. That if we have no magnetic fields, we have this prediction of close to breakup. And then if we consider in this primordial disk dynamo amplifications, if the dynamo amplification is not very efficient, then we just reproduce the no magnetic field curve. We stay at high rotation. But if we have a more efficient dynamo, then we get into a different branch of this evolution and could in principle very rapidly break the rotation. So maybe we have a bifurcation into slow and rapid rotators, but all of this is really uncertain. The entire MHD effect, and of course we will have a talk by Henk Sprout at the end of the meeting, who of course knows everything there is to be known about angular momentum transport because of MHD talks. So just wanted to mention this. Rotation in POP3 stars greatly matters for evolution on the Hertzsprung-Russell diagram, the internal structure, maybe promoting mass loss, how do the first stars die? And just to mention a few things, this is this was a seminal paper by Yoon et al. Where they present a nice summary diagram of possible end states of rapidly rotating massive POP3 stars. And so basically, here's the rotation rate, here's the 0H main sequence mass, and there are two important messages here. The first is there's an island if we have sufficiently rapid rotation where we may enable chemically homogeneous evolution. Which of course is very important for many aspects of how the first stars impact cosmic history. And then also just to mention this, if you look at what's happening here, the pair instability supernova, then we see that with rotation, these boundaries for the pair instability supernovae are shifted towards lower masses. So it's clear rotation has a super important role for the way that the first stars die. Also, just to mention one other important thing, and this gets me to a recent beautiful paper by Laura Murphy, and of course the Geneva group, and this is a study of the evolution of massive rotating population 3 stars. And one point that Murphy and I make is that there is sort of this basic picture that if you have primordial stars that don't have because of the lack of metals, they do not have radiative mass loss, then what happens is that there is a pileup of angular momentum at the stellar surface. And then here in this plot, Murphy et al. Show the angular velocity as a function basically of topological time. This is a fraction of hydrogen in the core. And then if you look at what the models show, then there's rapid spin up. And then when we hit critical conditions, there's a mass loss episode, some kind of mechanical continuum driven mass loss. And then there's a spin down, but the star very rapidly recovers. So there's this issue of that rotation in the first stars can trigger effective mass loss. And then just to finish this up, to have one idea where then again, Boyon Liu, who is a student of mine, we have teamed up with Geneva, with Yves Sibony and Georges, We have pushed this framework of possible mass loss from rapidly rotating POP3 stars to the limit. What we just assume is that we do an idealized experiment. We just assume that somehow winds, in the spirit of the earlier figure that I showed from Murphy et al., that winds are very effective in losing mass towards later stages of the POP3 stellar evolution. And then what we find is that in this case, if you plot the ejected carbon mass as a function of initial mass, so then just sort of let's look at this curve here. Then we find that for certain parameter choices, winds can enrich the neighborhood with a significant amount of carbon, that then gets us into the interesting thing of having another possible pathway towards explaining these incredibly interesting carbon-enhanced metal poors, CEMP stars, which are considered one of the key Rosetta Stones, so to speak, to probe the early universe. There's a bifurcation of metal poor stars that have normal carbon abundances, and then there is a large class of metal poor stars that are carbon enhanced. The traditional explanation is faint supernovae. So if basically all the heavy stuff is gobbled up in the black hole, only the light stuff, carbon, oxygen, maybe nitrogen, is spit out. But now we have, in this latest paper, we have an alternative possible origin for those stars. Again, right, then if one looks at the carbon abundances, right, these blue curves here, these blue points show our results. In principle, we can produce the signature. So maybe there are multiple ways to explain this carbon abundance. So all of this really just shows that when we think about closing the final gap in our cosmic worldview, first billion years of cosmic history, the role of the first stars, it is vitally important that we take into account stellar rotation, and this is largely unexplored. We also have to take into account magnetic fields and binary evolution, but stellar evolution is a key parameter. And with that, I thank you for your attention, and I'd be glad to take any questions.
Thank you very much, Volker. So the talk is now open for questions or comments. I look if I see hand raised. Maybe I have just one question for you, Volker. In the plot where you show the presence of the magnetic fields, and there is a slowdown, and the models without magnetic fields where you reach rapid rotation. The physics behind that, is it a fossil magnetic field? It is a dynamo effect? Where does the magnetic field come from?
Yes, that's of course the key question. And right, we have good reasons to believe that magnetic fields initially are very weak in the early universe, in the cosmic web, dynamically not significant, but so we have very weak seed fields, but then indications from analytical arguments, but also emerging MHD simulations of the POP3 star formation processes, that in the disk, in the POP3 protostellar disk, because of small-scale dynamo effects, we build up magnetic fields, and this could, in principle, be very efficient. So although we start with virtually zero magnetic fields, the universe and the star formation process likely will be back in an important MHD regime very soon, because of the small-scale dynamo. But of course, there are uncertainties, and this is really, as I said, very, very underexplored. It's just beginning to really look at this with real simulations.
Okay, thank you. Quick question from Norbert.
Yeah, thank you very much, Volker. Great talk, very interesting. So this idea to produce the Cemp stars in this way is very nice and a true alternative. I was exposed a lot to, low mass star people as well, especially in Holland, and they always favored Cemp stars be formed by binaries from AGB stars, which are also naturally producing carbon. What is the current status there? Is it clear how important massive stars versus intermediate mass stars would be to produce the Cemp stars?
Yes, of course, as you said, Norbert, right, the Netherlands, of course, is the center of this debate. But then, of course, right, this is right, there's by now, because also of the empirical evidence, right? There is the understanding that there are different classes of CEMP stars. There are CEMP stars that likely come from the low mass AGB binary scenario, and then right, the idea is that those are CEMP-S stars. We also should see S process elements, and then there are right, the idea is to probe the really first supernovae or the first enrichment events. More generally, we go to the CEMP no subclass, and then also there's some understanding that that when we get to the extremely carbon enhanced stars, right, carbon over iron of more than 100, then we also get into the regime that we favor massive stellar pathways. But it's a mixed phenomenology. But the good news is, right, the stellar archaeology, the data is coming. This becomes really quite high precision, and so there really is a hope to with this emerging deluge of data to sort out the question. But the idea is we need both pathways, AGB, binary origins, and the massive star supernovae, and possibly, right, our new idea of the winds. It's a mixed bag.
Thanks.
Thank you, Volker. Thank you very much. So we shall
Thank
go
you very much.
for the next speaker, who is Lionel Emerlet, who will speak about the rotation of supermassive stars.
So hello everybody. I hope you can hear me and see the screen. Can you see the
Yes.
PS? Okay, perfect. Okay, so first, thanks a lot for the invitation. It's really an honor to speak in front of people of you, even if you are not numerous. So I will talk about the rotation in supermassive stars. So it is a very different kind of object. It is at odds with most of the kind of star that we are used to think about. So in order to know what we are talking about, I will start with this plot, which is a recent extension from the famous plot by Heger and Woosley in 2002. So it has been extended recently in this paper toward the largest masses. So it shows the final fate of stars as a function of their initial mass. So this is for the case of POP3 stars, so without metals, without rotation, and without accretion. So this part of the plot is well known. I hope you can see my pointer. So it is known also that typically above 100 solar masses, the star is expected to collapse via the pair instability. And actually above initial masses of like 10 to the 5 solar masses, it is expected that these are the general relativistic correction that trigger the collapse before the pair instability, the collapse into a black hole. And so this is what we call, strictly speaking, supermassive stars. And the black holes that are formed by the collapse of this object are called direct collapse black hole, in order to refer to the fact that they are born supermassive directly. Okay, so of course it explains why we are caring about this object. It is related to the formation of supermassive black holes, in particular to the most extreme case, those at the largest redshift, at the highest redshift. So this is a sample of some of these objects as a function of the redshift. So this is the mass of the central black hole of the quasar. So these are quasars, galaxies in the formation process. So the mass of the inner black hole that has been inferred is typically above 10 to the 9 solar masses. And if we look at the most extreme objects, they are above redshift 7. So in this case, the age of the universe is smaller, is like a fraction of a gigayear. So it is clear that this black hole must have accumulated mass at an average rate of more than 1 sun per year. It is better if it is 10 solar masses per year. So there are not a lot of scenarios that allow us to trigger such inflows down really to the scale of compact objects. The most studied one is the case of primordial atomically cooled halos. So these are primordial halos that are devoid from H2, and so the cooling is less efficient, and so the halo does not fragment. It forms one central object in the center. There are also other scenarios like galaxy mergers that could trigger huge inflows up to 10 to the 5 solar masses per year. And so it is clear that the progenitors of this object are, they have to deal with accretion. They are probably dominated by accretion. And this is the reason why in the last decade, there are a lot of several studies that address the question of the evolution of supermassive stars and the rapid accretion, so really the rate of atomically cooled halos. So here it's probably the most famous one, the first study that really addressed this question systematically. So this is the HR diagram of some evolutionary tracks with various accretion rates, so constant accretion rate. So we can see the various tracks, and the important idea behind this is that above a given threshold, so above typically 0.1 solar masses per year, the star is actually evolving along the Hayashi limit. So it stays in the red. It does not converge towards the ZAMS, which is very important for the question of the radiative feedback. For instance, the ionizing feedback of this object while they are still accreting, it is expected to be negligible, which shows that it should not prevent further accretion. And so this is really an effect of accretion, of rapid accretion, as you can see by comparing the tracks. And physically, it is explainable by the fact that the accretion is so fast that the time it takes to lose the entropy and to contract, the surface has already been recovered by a significant amount of mass, so that overall the surface is still growing, even if each layer is contracting. So here are a few set of internal entropy profiles of my model that I computed with the Geneva Stellar Evolution Code without rotation. So also with this kind of accretion rate, I consider up to 1,000 solar masses per year. And so these are a successive profile. As the mass of the star grows, we see that the profile go to our largest masses. So this is really the Lagrangian mass coordinate. So we see that there is a convective core that grows in mass due to edge burning in the center. But most of the star, actually, you can see it's in a radiative envelope outside where the entropy grows. And more importantly, above a given accretion rate, actually, the evolution in the envelope becomes adiabatic. As you can see here, all the profiles are superimposing each other, which means that the layers contract, but without entropy loss. So we see that actually, in this case, the internal structure is well reproduced by a simple power law, which is called heliotrope, which is this one. And this is very useful in particular to address some question analytically. So we showed that actually in this kind of object, in the regime of extreme accretion, they become very simple objects. It's a bit like a polytrope, just with a different distribution of entropy. Okay, so what about rotation? So as you expect naturally, this kind of object, they are so massive that they are always very close to the Eddington limit. So it means that the luminosity scales essentially with the mass. And actually, the Eddington factor is always larger than 90%. It's typically 0.99 in the really supermassive range. So in this case, actually, as it was already said by Volker in the previous talk, so the real critical velocity is not the Keplerian velocity, which corresponds to the case of low mass stars, so which is the limit when just the gravitational and rotational acceleration cancel. When we consider a massive star, we have to account for all the accelerations. So this is called the omega gamma limit. And in this case, the maximum velocity, which is consistent with hydrostatic equilibrium, is lowered compared to the case without the impact of radiation. So here is so there is a new critical velocity, which is the second one, which accounts for the radiative acceleration. And compared to the first one, which is like the Keplerian limit, we can see that the second one becomes smaller. So the limit is stronger when the Eddington factor approaches 1. And really in the limit, so this is the Eddington factor, in the limit when it goes to 1, the second critical velocity goes to 0. So really for stars that are in the limit of, in the Eddington limit, the maximum velocity goes to 0. So supermassive stars must be slow rotators. So when we try to apply this rule to the case of supermassive stars, if we have the Eddington factor as a function of the mass, we can find a maximum velocity for this object, which is consistent with the hydrostatic equilibrium. So we can see that this is very low for 10 to the 5 solar masses. It cannot be in excess of 10% of the Keplerian velocity, and it still decreases toward larger masses. So it shows that for these slow rotations, actually, the impact of rotation on the stellar structure is expected to be negligible. So for many aspects, rotation can be post-process toward the non-rotating model. This is the positive thing. The negative aspect is that actually it means that if we want to form such object that satisfies this constraint, we need a very strong mechanism to remove the angular momentum in order for, if you want really the mass to continue to grow, so the gas to continue to accrete on the star, it must satisfy this constraint, and other mechanisms must guarantee this. So this is a special case of the angular momentum problem, which is general to all star formation, even in low masses. And here it's just that it is much more extreme. So in order to see it in a bit more details, so here at the top, the first figure is the internal structure, so the Kippenan diagram in Eulerian version of one of these stars. So this is for one given accretion rate, typically the typical one of atomically cooled halos. So it shows the evolution as a function of the mass. So we have a convective core here when the star becomes supermassive due to H burning, the big radiative envelope. We have also actually a small convective outer zone which contain negligible mass. Here is the Eddington factor. So here is the limit then that I derived from the Eddington factor. So now, so this is the case without rotation, and now we can post-process rotation. So see how this model will rotate if we simply assume solid rotation in the convective core and local angular momentum conservation in the radiative envelope. Okay. So the idea is that meridional current will be negligible because these are slow rotators, and in addition, the timescale are so short that even shears also will remain negligible. So in this case, what we obtain is that here, this is the rotation velocity of the core and of the surface. So here there is a knee when the H burning starts and stops the contraction in the center. And then we see that essentially the core rotates with an omega, which is, this is logarithm, so 4 orders of magnitude above the surface one. So we can interpret it as a very strong differential rotation. So we just have to be careful that it's essentially the Keplerian velocity itself will change a lot from the surface to the center. And this is what dominates these 4 orders of magnitude. So, and so this is by assuming that the surface is always rotating at the omega gamma limit. So then we can derive from it what is the growth of angular momentum of this object as a function of time. And this is what we did here. So this is the blue line. And we compare it with the gray line, which is the Keplerian angular momentum. So the angular momentum that the gas would have if it's rotating at the Keplerian limit at the surface. So we see that this is 2 orders of magnitude, even less or smaller. So it means that we need to remove really the more than 99% of the Keplerian angular momentum in order to form this object. So these are really strong mechanisms. So we tried to test one of the processes that could participate to this angular momentum loss. So one of the things is that these stars, they are pulsationally unstable, so they should have a strong winds. It has been estimated that the mass loss are of 10 to the -3 solar masses per year for this kind of objects. So this is 2 orders of magnitude smaller than the accretion rate. So the mass budget is dominated by accretion, and the winds do not prevent the formation of the star. But on the other hand, it can allow to remove angular momentum. So we tried to use some prescription used for red giants. So in computing the Alfvén radius that gives the distance of the coupling. So we use this expression where eta is the magnetic confinement parameter that scales with the power 2 of the magnetic field. And by this way, we can compute the Alfvén radius, which is shown here. And assuming a given mass loss rate and the omega from the stellar model, we can know what is the magnetic field which is required to have the loss, the angular momentum loss that are required. And so we find a huge field. Actually, it's 10 kilogauss. So this is much higher than all what can be produced by such a convective envelope. On the other hand, this is close to the largest magnetic field that have been detected in massive stars, which are expected to come from primordial origin. And this is consistent with a primordial magnetic field that have been kept frozen during the collapse, the formation of the object. So this could be one way to remove really the last part of angular momentum. There are many other aspects like gravitational torques in the disk that should be very efficient also to remove this angular momentum. So this is not a problem which is solved, but there are many ingredients that are proposed. So yes, another aspect, which is the one for which maybe the rotation plays the most important role in this object, is the question of the Gerund stability. So in the beginning of the talk, I said that supermassive stars are stars that collapse via the general relativistic instability. So now we'll try to explain rapidly a bit more what it is. So if you take the laws of gravity in general relativity in the most general way, these are the Einstein's equation here. If you consider the spherical case, in the simplest case, you just assume that there is no matter. So yes, the Einstein equation relates the Einstein tensor, which gives the trajectory of the particle, to the impulse, the stress energy tensor, which is related to the content of the universe. So if we just assume empty space, it means that T is 0. We obtain a very famous result, which is the Schwarzschild metric. If we just want to complexify a little bit, we add matter, but we assume it is in hydrostatic equilibrium. In this case, we obtain the correction to the hydrostatic equilibrium equation. So this is the TOV equation, which is used for neutron stars, essentially. And actually, if we just want to complexify by one step further, we can add hydrodynamics, but we keep only first order terms, and it was done by Chandrasekhar in 1964. And in this case, we can find the pulsation equation that leads to an eigenvalue problem, and we can find a sufficient condition for the instability with this equation. So this is for a global pulsation with a frequency omega. If this equation says that omega square is negative, it means that the star is unstable. So this is the general expression. And if we restrict ourselves to the post-Newtonian limit, we obtain this expression. So we see that there is a positive term, which is proportional to beta, so the ratio of gas pressure to total pressure, which expresses the departure from the Eddington limit, and the negative term that scales with the GR correction. And so when the negative GR term is larger than the positive beta term, it means that the star becomes unstable. So the larger is the mass, the smaller is beta, and the bigger is the GR correction. So actually, I tried to apply this method to know the stability limit of stars under the assumption of heliotrope. So in order to have a really analytical model. And yeah, so maybe I will just first present this plot. So this is the mass of the star as a function of the mass of the convective core. So everything is above the gray line, which is the identity. So we have a set of 5 tracks. These are models that I computed with the Geneva stellar evolution code with various accretion rates. And first, actually, I applied the Chandrasekhar equation to this model directly, and it gives the limit of stability indicated by the points here. And then I tried to compare with the model, the heliotropic model, so analytical models with various convective core. And this is the limits that I obtain with various central temperature. And actually, very rapidly, if you want to really be precise, if I take the same central temperature in my heliotropic model that in the last table model of this one, I really find the same limit. So heliotropes are a very good approximation for any rate which is larger than 10 solar mass per year. Okay, now this is without rotation. And if you want to include rotation actually in the treatment of the Gerund stability, the simplest way is to first start in the case of slow rotation. So if we consider a star in slow rotation without any GR correction, we obtain a pulsation equation which has this expression that we can compare with the post-Newtonian version. And so it is clear that if we have small rotation term and small GR correction, the cross term will be negligible compared to these terms, and we can just add everything to have one criterion. Okay, and in this case, actually, so here is the same plot that I did with several mass limit obtained with various rotation rate. So this is the ratio of the rotational energy to the gravitational energy. And I tried to assume several values for the angular momentum which is accreted as a function of the Keplerian angular momentum. And these are the red lines that are shown here. So we see that even if the gas is 1% of the Keplerian angular momentum, the accreted gas, already the shift toward the stability limit is already by several orders of magnitude in mass, you see. And yeah, so then, of course, the maximum value of f, which is consistent with the omega gamma limit in the various rates, this is something that I cannot constrain with this model. But if we keep in mind that for the case of atomically cooled halos, it was typically a value of 0.3%, like I said in one of the previous plots, we see that in the case of atomically cooled halos, actually the rotation can increase the final mass by only a factor of a few. But if in other cases we can find a way to accrete more mass, more angular momentum, actually, there is the typical limit that we can expect is above 10 to the 8 or 10 to the 9 solar masses. Above this limit, it will be harder because just the surface rotation, which is allowed by the omega gamma limit, is of the order of 1% of the Keplerian velocity. So this is really impossible to go way above. Okay. And so there are many uncertainties in these models. This is based on heliotrope, on the local angular momentum conservation in the radiative envelope. And these are things that are made to be corrected. But already we can see that with a small amount of rotation, actually, the stability limit of supermassive stars is increased significantly. So it might be that the most massive stars that exist in the universe, the limit to their mass is given actually by rotation. So this is my conclusion. I'll leave you with my last slide. So thanks.
Thank you very much, Lionel. And so the talk is open for discussion, for question. So Chris, and after Miguel has a question. So Chris first.
Hello, everyone. So I was just giving a talk on the other session on GW 1905-21, and I got a question that I would like to pass to Lionel. I got a question, given only the black holes that are made by stars, what's the maximum mass of a black hole that's still physical?
By stars, I mean, there is
a stellar origin black hole. What's the
really the most extreme case is 10 to the 9, you know. I mean,
so you think the star could make a 10 to the 9 solar mass black hole?
In a very extreme case.
Yes.
Actually, I'm sure that above it will be impossible. And in between, I have made some model with many assumptions that point this 10 to the 9 as a limit.
Okay, what puts the limit at 10 to the 9? What is the limiting factor? Time, or it's accretion, or
it's the Gerund Stability actually.
So that
is the fact that above a given mass, just the GR correction will be big enough to trigger the collapse. And it's only rotation that can prevent this. So it's all a matter of how fast it can rotate. It's really it's what's summarized in this picture. So you know, I use F as a free parameter, and then I need many other things to know which value will be the largest. I'm sure that if the mass is above 10 to the 9, it is impossible that F is above 1%. So this is why I say it cannot be above 10 to the 9.
Okay.
Yeah.
Thank you very much.
You're welcome.
Sorry, Miguel. I have my mic.
Okay.
Go ahead. Sorry.
Just a small question. When you said when you were talking about the pulsational mass loss, you said that there was ongoing accretion and at the same mass loss. So are you thinking that this is a spherically symmetric, a non-spherically symmetric situation where mass loss and accretion proceed through different latitudes, for instance?
Yeah, probably I expect more rotation, I mean accretion through the disk, so in the equatorial plane. And of course, it is probably not be a thin disk. And really, honestly, the detailed geometry close to the stellar surface, it's something which is not known even for normal massive stars. There will probably be also some funneling by magnetic field. And in all the methodology that we use, we still follow the accretion from a disk. Like for instance, in the accretion of entropy, we assume that it is the same as the one of the stellar surface. And so indeed, this is the picture of accretion through the disk and pulsational mass loss through the other direction. But of course, this picture is very naive because the disk will be probably very thick. And but this is the idea.
And if I may, just a quick thing. Is there any possibility that you may lose more mass than gain, or that they are comparable?
Yeah, actually, there are possibilities, for instance, in POP1 supermassive stars, because here I already talk about I only talk about POP3 supermassive stars, but in some extreme scenarios of galaxy mergers, there could be also POP1 stars, and in this case, there will be much more metals, and we just don't know what is the mass loss rate in this case. This is one of the numerous effects that we still have to look at. But yeah, this is not really an absolute limit, this 10 to the -3. It's for the typical case of POP3 stars of atomic in the condition of atomically cooled halos, that it will be 10 to the -3 solar masses per year. But, It might be that there are much stronger mechanisms in other cases.
Thank you, Lionel. So we are a little bit delayed, but it's not a problem, just 10 minutes for the moment. So please, Miguel, you can take the floor.
Okay.
Thank you very much.
So,
I have to stop.
Yes.
Sorry, yeah. I was looking for the button, sorry.
do you see my screen?
Yes.
Okay.
Perfect.
Well, first of all, let me thank George for the kind invitation to talk here on the dependence of magnetic fields and rotation of massive stars in the properties of the compact objects that they may produce. Why doesn't, okay. So what we know from a few groups working in the field, and I'm sorry if you are not listed here, I mean, are in the audience, that from stellar evolution calculations of similar fast rotating low metallicity stars with masses in the range 35 to 40 solar masses, but with different, let me call this, refer to them in this way, recipes for mass loss, they systematically predict relatively fast rotating cores at collapse. These are, for instance, here on the left, the specific angular momentum distribution for a 40 solar masses, very low metallicity star. And this is for a 36 solar masses, a star with 10% solar metallicity from Boosely and Heger. And inside in the inner core, the magnitude of the specific angular momentum, it's relatively similar with, of course, natural variations, but close to in order of magnitude in all cases. And explosion types and the central engine formation depend, of course, on the recipes that one employs in a stellar evolution for mass loss, angular momentum transport, and magnetic processes. And our goals in the long term are inferring the properties of stellar progenitors from those of compact remnants, which are left after core collapse, employing multidimensional neutrino relativistic MHD simulations. The focus of this talk would be on relatively fast rotating models with different degrees of magnetic energy and low metallicity. So those are likely progenitors of long gamma reversed or superluminous supernovae. In particular, we will try to address which is the explosion feedback on the compact remnant properties and what's the dependence of the type of central engine that you may form, either a protomagnetar or a collapsar, on the stellar conditions. So which is the genetic heritage of the compact objects. So for that, we have prepared or have made a set of 2D and 3D models. Let me first go to the 2D case, where we have considered a couple of cores, both of which with 35 solar masses. In other papers, we have just considered 20 solar masses and other masses. And these cores come from a paper from Boosely and Heger in 2006. Those are model 35 OC and OV. Both have low metallicity, 10% solar. They have large iron cores in excess of 2 solar masses, and they are fast rotating. And the difference between the two is the mass loss rate parameterized by this m dot parameter, which is larger in the case of OB, so that its final mass is 21 solar masses at the pre-supernova link, than in OC, whose mass at the brink of collapse is only 28 solar masses. In both cases, stellar evolution includes rotation and the effects of magnetic fields accounted for the Tyler-Sprout mechanism. In panel A, you have the distribution of a specific angular momentum in black of model OC, and in panel D, you have the specific angular momentum profile for model OV. So these two cores have a compactness ratio set at 2.5, which is 0.49 and 0.56 above the limit set by O'Connor and Ott in 2011 to let these models to achieve a successful explosion. But as you will see, most of these models explode. And when I say most of these models, what do I mean? What I mean is that we take the stellar evolution 1D simulation and we have to map it into 2 or 3D. This process is not unique, and we can do it in different ways. For the rotational velocity, what we take is the original rotational velocity profile of the star in most cases, although in some particular models, we just artificially lower the rotational rate by a uniform factor of 4, and in other cases, we just rise it by a factor of 1.5. For the magnetic field, we have two possibilities. We either pick the magnetic field as it comes from the stellar model, and this is our reference model, RO, right? Where, as you can observe, the toroidal magnetic field is the dominant magnetic field component, 10 to the 12 Gauss, of the order of 10 to the 12 Gauss at the core, while the poloidal magnetic field is subdominant. So over this basic model, we can, for instance, rise by factors 2, 3, and 4 or more the poloidal magnetic field. But in any case, except in this case, which is in equipartition with the toroidal field, the rotation, the magnetic energy that we add by this amplification, artificial amplification of the toroidal field, so the R component in a stellar evolution, is very minute compared to the overall rotational magnetic energy. In 3D, we cannot run so many models. We run a subsample of them. One of which is where we have artificially lowered the magnetic field to have some kind of reference hydrodynamic model. And then the other three models are, they have the same counterparts in 2D, and they have undergone the same process of mapping from 1D to, in this case, 3D. Right, so the general result when we take stellar rotation and the stellar magnetic field as it comes from stellar evolution is that in 2D we form a supernova explosion in spite of the large compactness of this model, which is mediated on a more or less equal footing by neutrinos, magnetic fields, and rotation. The explosion has a considerable magnetic contribution in as much as it helps for the collimation of the outflow along the polar direction. Here you see a distribution of the electron fraction, YE, and you observe how the form by rotation is this protoneutron star that results after the collapse of the inner core of the star. This protoneutron star grows in mass, as can be seen in this graph over here, which shows the mass of the PNS as a function of time plus bounds, because there is ongoing accretion along the equatorial regions, while at the same time there is an outflow which goes along the rotational axis of the system from matter which does not finally end up in the PNS. It comes from the equator and may eventually be channeled out, or mass which is just dragged along away from the outer skirts, less loosely bound of the PNS. Anyway, this PNS grows by the balance between accretion and ejection of mass, and at some point it goes over the limit set by the equation of state, in this case Latimer's UST220, which sets a baryonic mass limit of 2.45 solar masses. So this model keeps running and eventually may produce, we see that, a black hole with more than 3 solar masses, a bit more than 3 seconds after bounce. So this model is going to produce a black hole, and since there's a lot of specific angular momentum in the outer layers of the star, eventually after about 10 seconds, an accretion disk may be formed around that black hole. So we have all the elements in 2D to make a collapsar. Doing the same model in 3D, we have not been able to run so long in time, but we observe that the growth of the mass of the PNS is much moderate. And indeed, it tends to flatten. So the prospects for black hole formation in 3D are not so clear as in 2D. An extreme case is where we just take a stellar rotation and an enhanced magnetic field, poloidal and toroidal components in equipartition. In this case, we obtain a very prompt magnetorotational explosion because magnetic fields launch jets along the polar axis before neutrinos can achieve to do anything. The protoneutron star, of course, is very oblate, and what is more important, it stops growing after about 400 milliseconds. And this is not only in our case, also the Sart and co-workers observed this maximum mass, and after which the mass of the PNS starts to decrease. This is because the magnetic stress is so intense on the outer layers of the PNS that those are just dragged along the ejecta in the polar direction. This is a robust result in 3D. Here in the lower panel, you have the mass evolution of the same model. This yellow line here corresponds to this green line over here, and you can clearly notice the maximum in mass in this case. So since this model is not going to form a black hole, and we have a relatively heavy proto-neutron star, which is very magnetized, indeed with magnetar field strengths, what is expected in this case is the formation of a proto-magnetar in addition to a supernova, which might explain either some hypernovae or superluminous supernovae. Looking at the explosions that we have among our models, we have a diversity of possibilities. Most of our models explode, though they achieve shock revival by different mechanisms. For instance, we have models where the rotation has been reduced with respect to the original stellar progenitor, which explode by the standard neutrino-driven mechanism aided by hydrodynamic instabilities, and eventually produce a black hole. This is the case of the model in panel A in 2D, where you see that it produces a very asymmetric supernova in 2D, not so much asymmetric in 3D. Rapid rotation creates conditions for the generation of bipolar explosions in models where we have not modified neither the rotational profile of the star nor the magnetic field structure and strength. And this is because the proto-neutron star, whose surface you can more or less identify with these pink isolines here, which mark the neutrinospheres of the proto-neutron star, they become so flat, close to the rotational axis, then by geometry, the amount of energy released by neutrinos per unit time and unit mass is 100 to 1,000 times larger around the polar axis than in the equatorial regions. And thus you produce, for instance, you can look at this panel B here, also very collimated ejecta. And this is robust in 3D, this is the same model run in 3D. Also, we have early magnetic rotational explosions when the magnetic field is in equipartition, colloidal and toroidal components. And in this case, we can reach even within the star velocities up to 1/3 of the speed of light. And the ejecta energies are already reaching of the order of 10 to the 52 ergs, which place these models in the ballpark of hypernovae. These jetted explosions are a solid result in 3D models, including MHD, and different degrees of sophistication for the neutrino transport across the literature. If we look now at the compact remnants that we have by looking at the mass evolution versus time in 2D, you see that there is a bunch of models which cross over the limit of set by the equation of a state. So these models eventually, and sooner or later, will collapse to form a black hole. In some cases, we see black hole formation. In some others, we have not run sufficiently long these models to see that, but they will do. But you see also another set of models which have a growth of the PNS up to about 0.4 seconds, then a local maximum, and the subsequent evolution it's varied. It depends on mostly the strength of the poloidal field component. So for the strongest poloidal field component, the mass tends to decrease with time significantly. For models where the poloidal field is just twice as large, and in the stellar evolution model, which is this red line, you see how much different the evolution is by changing by a factor 2 the subdominant magnetic field component. You see that this doesn't cross this limit, so they keep us rotating proto-neutron stars for very long, and the evolution is non-monotonic. I stress that this is nearly 10 seconds of evolution post-bounce. And the evolution is non-monotonic because eventually the stresses, magnetic stresses, are so strong that start to extract more mass than it's secreted into these compact remnants. Now, you can also see a division between models that form black holes and neutron stars in terms of how much rotational energy it's in the PNS. Below 6 times 10 to the 52 ergs is the typical energy for protomagnetar candidates or models that may yield protomagnetars, and above that limit for black hole forming models. If you form black holes, the spin of those black holes, it's very different, depends on the exact modifications we have done on the rotational profile and on the magnetic field, but the spin prediction is between 0.1 and 1, so basically anything you want. And for the magnetic field at the surface of the PNS, in those models which are run for longer and will produce protomagnetars, you see that they are on the order of 10 to the 14 or nearly 10 to the 15, depending on the model. So magnetar field strength. The poloidal magnetic field strength, it's an ordering quantity. This poloidal magnetic field strength from the stellar core, from stellar evolution. Larger poloidal field means a smaller mass of the remnant. And here you see an ordering according to poloidal magnetic field. Also, a larger poloidal field brings larger explosion energies and as well faster propagating shocks. In 3D, the accretion through the equator is significantly suppressed with respect to 2D, and thus the mass of these models do not grow so much as in 2D. Let me just comment quickly on the fact that the angular coherence length of the poloidal magnetic field, it's important to settle the outcome in terms of compact remnant and explosion. We have just considered the same initial star, and we have considered several realizations of the magnetic field topology, either a dipole, a quadrupole, an hexapole, or an octapole, so increasing number of multipoles. And the effect is clear. The more multipoles you put, so the smaller the coherence, the angular coherence length of the magnetic field, the more likely is that you will form a black hole, and the explosion energy will be smaller, right? And let me end saying that in spite of their high compactness, our cores develop successful super neutrino-driven or MHD-driven supernovae. The feedback of the explosion dynamics on the compact remnant works as follows. There is accretion along the equator, making that the mass of the PNS grows, and decrease of the mass because of ejection along the rotational axis. In some cases, the protoneutron star collapses further to a black hole, at times in less than 2 seconds after bounce, and a fraction of these models will form collapsers. You need to form also an accretion disk, and this is not guaranteed. It depends on what's the specific angular momentum in the outer layers of what remains in the star. I remind you that the equatorial region is non-exploding and it's still falling in most of our models. Models without a black hole contain rapidly rotating, flattened, and strongly magnetized protoneutron stars. These models are likely candidates for massive, if you wish, protomagnetars, because many of them have masses of the order of 1.8 to 2.2 solar masses or so. There's a strong dependence on the magnetic field topology, coherence length, and dimensionality of the stellar evolution model. In 3D, our models confirm the explosion type found in 2D. They still be missing some numerical resolution to give the concluding results, and especially longer evolutionary times, but this is costly in 3D. Accretion onto the PNS is strongly suppressed in 3D, and no black holes have been formed so far. And let me just flash some consequences for stellar evolution models. Cores with angular momenta smaller than that obtained typically by 1D stellar evolution calculations form black holes, and eventually may produce collapsers if the angular momentum outside of the core is large enough. Stellar cores with the distribution of angular momentum, which is prototypical in stellar evolution calculations, including magnetic torques and moderate to large mass loss rate, form protomagnetars. And there's a strong sensitivity to the radial magnetic field component, and thus we need a better treatment of magnetic torques in especially convective layers, something which is missing in all the stellar models that we have been considering, and maybe something along the lines of Takahashi and Langer, it's a good idea to start incorporating these effects. Thank you. Thank you very much.
Thank you very much, Miguel. So, yes, Hazaf, Pierre, you can go ahead.
Excellent talk. Question: can you comment on the prospects of producing a gamma ray burst in these models? And sort of continuation for that, you were mentioning that in some fraction you might produce collapsars. Did you try to run it for long enough to see if you can actually produce a gamma ray burst, and if you can get what's the role of a Blandford-Knight process in producing the explosion?
Okay, starting by the last question, we cannot do Blandford-Knight because it's not general relativistic code, but we have run our models for nearly 10 seconds after bounce, and this is very important because, well, this plot shows this is the typical plot where you just display the specific angular momentum of the star and the angular momentum in the last stable circular orbit of a Kerr black hole with the same mass content up to that mass shell and angular momentum contained up to here. So where the red line is below the black line, you can form an accretion disk, naively speaking, okay? So for instance, we have estimated that the free fall time or the disformation time of this mass shell onto the core for the reference model would be of the order of 10 seconds. We have run up to that time, and we have not seen yet the formation of an accretion disk. And this is because the feedback of the shock in the equatorial direction, which is just preventing free fall of this matter. What does it mean? It means that if you form a disk, by the time you form the disk, the ejecta of the supernova would have reached the surface of the star, and it would have broken out. Whether you form a collapsar or not, understanding that this means disk formation, it's still unknown. We would need to run even longer, but this takes quite a lot of computational resources. If it's because of Blandford-Knight, well, it could have happened in the case of the reference model because it forms a black hole at about 3.5 seconds after bounce, and the magnetic fields are strong enough. But the densities still are quite large to allow for a relativistic outflow. So the prospects are not bad, but I would say that we cannot totally answer this question yet to form GRBs.
Thank you.
Thank you very much, Miguel. So we have now to go ahead, and the next talk will be by Chris Belczynski on low effective spins of LIGO-Virgo binary black hole mergers.
Let me just enter the slideshow. Can you guys see the slides and hear me?
Yes.
Thank you very much. Thank you very much for the introduction. So I will talk about effective spins of LIGO-Virgo black hole mergers, which we have plenty of right now, and we'll have even more of them. And for me, it was quite a surprise that, majority of those effective spins, which are kind of a measure of black hole spins, are very low. So let me first make that remark. What I will be talking about refers to black holes that are made out of stars. So it will apply almost equally well to isolated binaries and formation of double black holes from isolated binaries, as well as to cluster formation of double black holes. It will not apply to primordial black holes that are not formed by stars. They do have the primordial black hole community, they have their own means of producing low spinning, high mass black holes, but I'm not gonna talk about this, okay? So let me lay out the problem. And I'm gonna start with 01, 02 because picture is more clear, but I will move on and I will expand to 03 to show you the small differences that we find in 03 on my last slide, okay? Oh, and I was about to start the clock because I know we're running short on time, so I will watch my time. Okay, so we had in 01, 02, we got exactly 10 double black hole mergers, but about all of them, almost all of them, maybe modulo 1, are consistent to have low effective spin, and actually that effective spin is consistent with being 0. Effective spin, it's a mass-weighted projections of binary black hole spins on angular momentum axis of entire binary. Okay, so if black holes are spinning maximally and they're aligned with angular momentum spin, the effective spin parameter is +1. If they're anti-aligned, the spin parameter is -1, and when you have them in different combinations, it's anywhere between -1 and +1. And it appears that all of them are pretty much consistent with 0. So you can have pretty much three setups in which you can produce a 0 effective spin. The first one is when black hole spins are spinning maximally or are high spinning, so you just put them in the opposite directions, so they cancel out. And then that formula for effective spin becomes 0. You can put both black hole spins in an orbital plane, and then those cosines projections are 0, okay? Or you can have the third situation that actually black hole spin magnitudes are 0. And I'm gonna work on the third options. I think this is the most natural explanation why those spins or effective spins of LIGO black holes are low. It is that black hole spins that are produced from stars are small. So that may kind of go against what electromagnetic observations seems to be telling us. We have some electromagnetic estimates of black hole spin in high mass X-ray binaries, and I give you here a couple of examples, and they're all high. M33X 7.8, LMC X 1.9, Cygnus X1 larger than 0.99. Okay, but we don't know if those are measurements. Those are not actually measurements. Those are heavily caveated estimates, and we don't know if those are real or not. Okay, but I can come back to that during a question if you do have questions about it. So how I'm going to proceed with that? So I'm going to use stellar evolution models to predict effective spins of double black hole mergers. So I'm going to do it the following way. We're going to assume some initial rotation of massive stars, which we do measure. We see massive stars in galaxy LMC. We can measure the rotation, so we have an idea here. Then I'm going to follow angular transport I'm going to follow the transport through the evolution of the star until the star collapses to a black hole. Once the angular momentum is being transported to the surface, it's being blown away with stellar winds. And again, we do have, okay, it's highly uncertain, but we do have some estimates of wind mass loss for massive stars, okay? So I'm going to assume some model. And then I'm going to do core collapse. I'm going to collapse the part of a star that, according to our current knowledge, is supposed to collapse to form a black hole. And here you can have supernova explosion, you can have some mass ejections, but for most of those LIGO massive black holes, I'm going to assume that entire angular momentum and entire mass goes to the black hole. So it's kind of simplification, but it's probably pretty good for those high mass stars like 50, 60 solar mass stars. We're not talking about stars like Miguel was talking about that would give neutron stars or low mass black holes. So we're talking about mostly those heavier stars that produce massive 20, 30, 40, 50 solar mass black holes, okay? So the only problem that I'm gonna touch here, just to isolate the problem, is angular momentum transport. I'm gonna see if I can use that LIGO astonishing kind of observation to me that those those effective spins are low, can I actually constrain angular momentum transport within massive stars. So I'm going to assume two models, actually three models, but I'm showing only two models here. So this plot shows, I'm sure you guys know those type of plots, specific angular momentum of star, which is 32 solar mass star at low metallicity as a function of mass coordinate within a star. That plot shows various models at the end of core helium burning. So pretty much top lines, those top coral lines that are about order of magnitude above bottom lines, I have assumed here angular momentum transport very inefficient by meridional currents. And I have used Geneva code and I use George's models here to produce those type of curves. Bottom lines, bottom curves correspond to Tyler-Sprout magnetic dynamo to efficient angular momentum transport. And I have used MESA to produce those curves. Now I have some prescriptions that I know which part of the star I want to collapse to the black hole. So I can calculate a black hole spin parameter. Okay, I can get a spin angular momentum J over mass of a black hole square, and I could get a black hole spin parameter for every star in my simulation. So I'm gonna do, so of course we've done a bunch of models, not only one star. So on the left-hand side, you see a black hole spin on a vertical axis versus mass of a CO core at the end of stellar evolution. Mass of a CO core is pretty much a mass of a black hole. It's a proxy for black hole mass. So for Geneva models, we predict, for mild angular momentum transport, we predict black hole spins somewhere between 0.2 and 0.9. This is a dimensional spin parameter, J over mass of a black hole squared. For MESA models, for a Tylor-Sprout magnetic dynamo, spins are about 0.1, and this is shown on the left, on the right-hand side plot. Note the change of a scale. Here is from 0 to 0.2. On the left-hand side, from 0 to 1. That's why they look kind of similar, but they're not. So high spins here, low spins for effective angular momentum transport. This is, fully expected. But we actually get a measure that depends on the mass of a star and its metallicity. And we also adopt an ad hoc model. We take the model from Jim Fuller, who has a very effective angular momentum transport, and pretty much any black hole, no matter what mass of the initial star, no matter what metallicity, the black hole has almost no spin. Well, the spin is 0.01 when I talk to Jim. Okay, so we have 3 models. Now I'm gonna create 3 synthetic universes, and I'm gonna populate them with stars that differ just by angular momentum transport. Either they have a Geneva model transport, MESA model transport, or Jim Fuller model of angular momentum transport. I'm gonna evolve all the stars in the universe to present time. I'm gonna put a LIGO detector, and I'm gonna see what black holes I see, and I'm gonna try to, and I will actually measure LIGO effective, LIGO detective effective spin parameters. So I'm gonna show you the distributions for those models, okay? So this is one of my major results. I'm going to spend a bit of time on the plot, and then I have one more and then conclusion. So I'm going to try to keep myself to time. So on the left-hand side, the solid lines, the red line and magenta line, show a distribution of my synthetic double black hole mergers that I got from stars with inefficient angular momentum transport, with meridional currents. So when you look at whether magenta line on a red line, doesn't matter. Those 2 models just differ by black hole natal kicks. But that introduces no change in a conclusion. I'm showing effective spin parameter from -1 to 1 on horizontal axis, but on the vertical axis, I'm showing a detection weighted probability of a given type of merger with a given effective spin. And it's a logarithmic scale. And this is very important because when you look at the red line, most of the synthetic double black holes that I create in that synthetic universe has an effective spin parameter of 0.8, 0.9. This is totally inconsistent with the data, O1, O2 data, which is shown with the blue stars with the error bars on those LIGO measurements. It's totally inconsistent. It's given that it's a logarithmic plot. All my synthetic black hole measure have effective spins that are high. Okay, so now we switch to the right plot, which gets us another universe with all the stars are subject to high angular momentum transport, efficient angular momentum transport with Tylor-Sprout dynamo. And here you see again 2 models, red and magenta line, low black hole kicks, and magenta line, high black hole kicks. That's why I don't change a really effective spin parameter distribution. I only change how many double black holes I produce. Higher kicks, the lower number of double black holes. That's what you see, the change from red line to magenta line. But as you see right now, those distributions of effective spins peak at about 0.1, effective spin 0.1, and that's what the LIGO data from O1 and O2 is consistent with. So right now, from such a simple observations by 10 systems by LIGO, just from O1, O2, we can already reject one model of angular momentum transport and confirm another, okay? Now I'm going to replot that MESA model on the next plot and compare it to even more efficient angular momentum transport from Jim Fuller. So I'm going to keep just that plot here. So that I'm keeping the red line on the left plot. That's the same MESA model. I'm just keeping red line, same plot. And then I'm going to even more low spinning black holes for Jim Fuller model. So you see the distribution is even narrower, but still kind of consistent with LIGO data with error bars. So I cannot really tell between Jim Fuller model and the original Tylor-Sprout dynamo model, but I can tell that meridional currents is not enough in terms of angular momentum transport. Those two seems to be okay with the data, okay, at least with O1, O2. Now, when you ask how about O3, we have a 39 more double black holes, and we have some outliers in terms of effective spin parameter. So actually, most of them, 36 of them, are consistent with the blue data that I'm showing for O1, O2. 36 of them are still consistent with effective spin parameter being 0, or kind of slightly on the positive side. Okay, so major conclusion doesn't change with O3. However, a couple of outliers, and let me talk about the highest outlier that has effective spin 0.5. Error bar on that is about 0.2. So it's anywhere between 0.3 and 0.7. So that would be inconsistent with a red line with Mesa model and with a red line Fuller model. However, in those two models, I did not include tidal interactions. And tides are important because when you already form the first black hole, the second star after common envelope or after interactions will be nearby the black hole, and it will be Wolf-Rayet star, very compact star, so it can be very close. And the black hole, the first formed black hole, can invoke tides on the Wolf-Rayet star and can spin it up. Even if you have a very efficient angular momentum transport with Jim Fuller model, you can pump orbital energy into that Wolf-Rayet star and have it highly spinning, even maximally spinning, at the time of a collapse to the black hole. When you take that into account, you change the solid line on both plots to the dotted line. So you see, it's a logarithmic plot, so it's hard to read. But then if I include tidal interactions on my double black hole merger progenitors, I form about 20%, up to 20, 10 to 20, up to 10 to 20%, depending how well I want to spin up the stars. I form double black holes with effective spin up to 0.5, 0.6. So I can explain those things in terms of binary evolution. Or I can say, okay, tidal interactions do not work in binaries, at least they're not as efficient as I assumed here. And maybe such an event with such high spin, it's a second generation merger, two black holes merging in global clusters and catching another companion. So I don't know, I'm being here agnostic. You would think you have a proof of tides. No, maybe you do, but maybe such a merger with such high effective spin was formed by global cluster. So with this said, let me give you my conclusion. So the origin of those all 50 double black hole mergers is still unknown. I know it seems surprising. We have all those masses, various spins, we have objects in the first mass gap, second mass gap, and they still can be explained by isolated binaries or by global clusters. Also, primordial black holes. That community also claims that can explain pretty much majority, or if not all, those double black hole observations, okay? So we have another contender for the origin of those double black holes. Then that's pretty much repetition of the same thing. I want to go to the last point. What are the Astro implications we can get right now, besides general relativity and other technical, well, not science and technical issues like, developing LIGO instruments or so. For me, Astro implications are the following. There needs to be efficient angular momentum in massive stars, at least as massive as original Tyler-Sprout dynamo, maybe as efficient as Jim Fuller is predicting. Possibly tidal spin-up was detected if those double black holes are coming from isolated binaries, or possibly a second generation merger was detected if those double black holes are coming from global cluster channel. And I would like to stop here. Thank you very much.
Thank you very much, Chris. You have been very short, but it was nice because we are a little bit delayed.
I know, I see that.
Thank you. So Miguel has a question.
Yeah, thank you, Chris, for the talk. I have lost how you predict the spin of the black hole out of stellar evolution, because I think that this is one of the points I wanted to make in my talk. You don't have a one-to-one correspondence between the spin in the innermost iron core or 3 or 10 solar masses and the spin of the black hole. And I have many examples of very fast rotators, which end up with spins of the order of 0.1, 0.2, instead of maximally rotating black holes. So what are you assuming to reach this?
Yeah, so that's what I said. I'm taking a model, like specific angular momentum for a given star at the end of core helium burning, and I just collapse most of that star into the black hole, holding all the angular momentum in. So that's let's say it's an upper limit in that sense.
Okay.
Okay, and I would think that was my question. I wanted to ask you that question, but we were running out of time. My question was to you. I know that you were doing some ejecta of mass angular momentum for those low mass models, but let's say if you went to 60, 80, or 100 solar mass star at low metallicity, would you then, would you expect a lot of angular momentum ejection at the black hole formation or not?
Well, the thing is that this angular momentum is redistributed before black hole formation because of magnetic stresses.
But if you collapse entire star into a black hole, I mean, that doesn't matter to me.
Yes, of course, but there is a part of the star which just goes away in the polar
No,
direction.
but I'm assuming, that was my assumption up front here. I'm assuming that all the stars for those most massive...
Yes, okay. If you go to direct black formation and everything goes, yeah, you are absolutely right. I just meant that there is a intermediate regime of stars where this may not be the case.
Fully agreed, fully agreed. And that would be probably a good addition to our model.
Thank you very much. So since we are a little bit late, maybe we shall go ahead with the last talk of this session. And it's my pleasure to give the floor to Henk Sprout. So maybe, yes. We can see your slide. It's okay.
So do you hear me now?
Yes, absolutely. It's okay.
Okay, now I wonder how much of this you get to see because I'm just doing the screen itself instead of in.
It's okay. We can go ahead like this. It's we can see the slides.
Okay. Good. So this is about magnetic fields in differentially rotating stars, and the origin of the problems that we are talking about is this kind of observations from Astro Seismology, where it is seen that for subgiants here on measured in terms of the radius of the stars, and for giant stars, the cores are rotating somewhat faster than they would have done without some kind of angular momentum conservation, but still a factor of 10 lower than predicted by, for example, my recipe for angular momentum transport. So something is missing in the sort of recipes that we have used for angular momentum transport. And I'll try to sort of argue that this has to do very intrinsically with the behavior of magnetic fields in MHD at a very low basic level. And to make that clear, let me first start then by making the comparison with ordinary hydrodynamics in stars, where we have different mechanisms that do not depend on magnetic fields, and then show you why magnetic fields are so much different. It has to do with the fact that magnetic fields have a strong memory. By this, I mean that their behavior depends on for a long time on the history of what has happened to it. And it is not local either, because it can come from things that have happened at a large distance from the point where you're looking. That is a fundamental difference. Now, in order to sort of illustrate this better, I'll look also at a number of really crazy surprises we had in terms of angular momentum transport and accretion disks. So the simple form, hydrodynamic instability, overturning shear viscosity resulting from turbulent shear flow. The standard for this is Jean Poussin's 73 process. It is weak. It has been put in stellar evolution calculations, and it would produce rotation rates, core rotation rates, even a factor of 10 higher. So let me give then a little, okay, but we've just done that here. Okay, here. Contrast that with magnetic behavior. And as an example here, it's not directly relevant, but just to show what I mean. The case of the sun, you have a pole equator magnetic field, which gets wound up, as we say, by differential rotation until it becomes a mostly toroidal magnetic field, and then does some kind of instability that produces sunspots. Now, this is then a process where the whole dynamo cycle depends on basically the history of the magnetic field. And this is not the only case where this happens. So it turns out that a lot of interesting things have happened in the theory of the hydrodynamics of accretion disks. And though these points that I'm going to make were not usually heavily advertised, they have become unavoidable in terms of things that have to be done, or at least things that have to be understood. These are three problems. The convergence with numerical resolution. You would like to have your simulation converge at high resolution. Second, the dependence on the magnetic Prandtl number. I'll come to that, what that means. And then finally, the very curious dependence on the presence of an initial magnetic field of a particular kind. Now, as I said, not all of these problems were heavily advertised, but they basically played a role already very early on, where everybody got a different answer for the stress due to a magnetic instability. So let me start then with the dependence on numerical resolution. We have the case of an accretion disk. That's magnetohydrodynamics with differential rotation. Differential rotation is due to Keplerian rotation around, say, a black hole, radial coordinate r. And instead of doing the whole disk, we cut out a little cylinder of our actually a square box, and we put periodic boundary conditions in the radial direction as well as in the azimuthal direction, the original azimuthal direction. And in that box, we have then a Cartesian approximation to a little section out of an accretion disk. And we do this with periodic boundary conditions in the radial direction. That can be done including the shear in a standard way, the shearing box calculus, the shearing box method. So we have a shear rate sigma, which in units of the rotation is just Keplerian, the -3/2 dependence. So basic. I'm doing this wrong. This is from calculations that were reported already in 2007 by the group of Jean Papaloise, where the question was, well, let's take a simple case. We don't put a vertical stratification in this disk. We can take a little box, and we increase the resolution 64 cubed, 128, and so on. And we measure the effective stress, the magnetic stress that leads to angular momentum transport in the disk as a function of this resolution. And as you can see, from here to there, the resolution goes up by a factor of 2, and the stress goes down by a factor of 2. And at even higher resolution, it goes down even further. Now, this is strange. A mathematician will say, well, you obviously are trying to do a not well-posed problem numerically. So this was a concern. And it was quoted, but it was not followed up much until 10 years later, where a group of people did the same calculation with a different code and got the same answer. So this is not an arbitrary case anymore. Now people have found loopholes around this. If you take these boxes, not small, squarish, but if you extend them vertically, then the thing behaves different, and the codes can sometimes converge. Or you put in vertical stratification like actually exists in an accretion disk. So what do you do with this? Well, the practical answer is, of course, well, you take a taller box and you're done. Okay, but is that really an answer? Because as long as you don't understand why this strange behavior exists in a simpler case, can you really be sure that you understand the more complicated case? So the second is the magnetic Prandtl number problem. What's that? Well, suppose we have a viscosity nu in square centimeters per second and a magnetic diffusivity eta, and we take this ratio. So a high magnetic Prandtl number means that viscosity is stronger than magnetic diffusion and the other way around. Now in accretion disks, in the interior of a star, the kind of stars that you're interested in, as well as in the laboratory, this number is smaller than 1 or much smaller than 1. Okay, magnetic field diffuses faster than the flows. And under these conditions, it turns out to be very hard to get this standard magnetic dynamo that people find. It's called MRI dynamo, MRI turbulence, actually going. Now this was not, okay, let's show you how this came out. This shows you the Reynolds stress that is needed, the red curve, the Reynolds stress, the Reynolds number that is needed to get the dynamo acting at a certain value of the Prandtl number. So if that is 1, for example, you need a Reynolds number of at least 100,000 or so. And this was the end of the series. The question is, how do you extrapolate this? Because in stars, your Prandtl number can be a 10th, 100, 10 to the minus 4. What is the asymptotic scaling if it exists at all? You can also see this in a different way of representing it. This shows you that at least up to 10 to the 3 or 10 to the 4 Reynolds numbers of the order 10 to the 4, there have been no, these are all successful dynamo simulations, but none of them have exceeded beyond this line, Prandtl number 0.1. Nothing, no indication that you can get a dynamo acting at Prandtl number less than a 10th. Now there is an explanation for this, but let me skip that over. The third effect is the effect of a background field, also called a non-zero net vertical field or net flux in accretion disks. This comes about as follows. Go back to these simulation sets by Popoloizo et al. And we, instead of just assuming that the initial magnetic field was completely enclosed in this box, we assume that there are a number of field lines sticking through it here. Now, this is an important thing because the number of those field lines is fixed. It's a conserved quantity in these calculations as a result of the periodic boundary condition. Everything that moves out here is automatically put in on the other side. So this only depends on diff B equals 0 and the boundary condition used. Okay, this is just a number of references where this has been studied. Now, don't look too close at this diagram. This is the most interesting one, I think. But I've taken the liberty to formulate it a bit in terms of different quantities. These are plasma betas and alpha parameters. This line corresponds to the result that the final field strength of this dynamo scales as this initial field, this conserved flux magnetic field, to something like the square root 1/2 power. What does that mean? There's basically no clue. If I can. So this is in fact somewhat important if you're looking at a situation where the disk is not in the form of these little boxes with periodic boundary conditions, but if they're neighboring boxes that have their own behavior and that somehow manage to slip in some of this kind of magnetic field. That would be my suggestion how the connection between these different distances in the accretion disk might feed each other these weak fields, which then determine a strong final field. Well, don't take that too serious. It still needs to be worked out. So this is then the effect of this conserved flux has the following results. That the result that you get out depends on initial conditions. So this is not a true dynamo, the way we understand it. And on the other hand, it's not simple winding up of magnetic field lines in turbulence, because that would just give you a time-independent linear increase. So this is one of these other strange things that happen. So then our question naturally is, how do we translate this information to our case of a stably stratified stellar interior? I think the main thing that I would like to stress is that these funny things happening in accretion disk simulations show you that you cannot really rely on existing views and intuition about magnetic turbulence, period. Okay. Now, if you want to do better, you will have to do more numerical simulations because it's the only way in which we actually discovered these things. But I think I would submit that these better not be numerical simulations where you pack in everything that you know into your accretion disk simulation, because then in the end you don't even know the consequences of these funnies that have happened in simpler cases. So it requires, in my opinion, that you're able to pinpoint new questions that you can do with limited, typically can do with limited, more limited numerical work. And there's a few things that I could suggest there. But basically, let me just then give my conclusions. In MHD, the long memory of the magnetic field destroys analogies with hydrodynamics. What I mean by long memory? Well, if it basically it boils down to the fact that at high magnetic Reynolds numbers, everything happening has a long history of winding up and so on before magnetic diffusion starts destroying it. So there's a history attached to this magnetic field that you cannot capture easily in an initial, in something that would be independent of an initial condition. So the current results show these three problems: the lack of convergence, numerical convergence, magnetic Prandtl number dependence. It doesn't work for Prandtl numbers less than 1/10, at least not for Reynolds numbers that so far have been able to be considered. And then we have this funny conserved flux problem. So in order to proceed, I think it's important to actually acknowledge this problem. In most of the history of these accretion disk calculations, people have said, well, there's this problem, so somebody, such and such a group gets an alpha parameter for a momentum transport of 0.01. We get 0.1, okay. That's the sort of level of discussion. this has improved, I must admit, but there is really this tendency to get nicely expanded realistic simulations at the cost of learning, but actually these problems make life so difficult. Okay, stop there.
Thank you very much, Hank. The talk is now open for a few questions. And I see Miguel who asked a question. Yes.
Yeah, Hank, you ask, you say that one has to formulate better questions. Which are those better questions that you you can ask to numerical models?
Well, for example, if we want to do stars instead of accretion disk, then of course the geometry has to be a bit different. I would say what would be quite useful is to have some kind of simulation, preferably in spherical harmonics, that can address efficiently a spherical shell with radial differential rotation in it. That Domenico Midori has tried to do that with the codes that were available at Toulouse, but there was a problem there. It probably needs adjustment of the code. That would allow you to efficiently see whether something like the ingredients I put into the Taylor dynamo, whether those actually work out in numerics. And the other is on a more sort of at the level of these problems that I mentioned. People have considered the effect of these conserved flux and Prandtl number depends. But what if you combine them? For example, does this magnetic Prandtl number disappear if you add a little bit of magnetic field? Yes, probably. But how does that interaction work? Okay, that is something that can be done with standard MRI simulation boxes. So those are the two that I can imagine at the moment.
Mm-hmm. Thank you.
Thank you. I think that it's already late, so we shall probably stop here. I would like to thank all of you who have participated either as a speaker or as a public to these talks. It was short, it was dense, and it shows at least that these problems of stellar rotation, which is very old, it begins nearly with Galileo when he saw the rotation of the star with the spots, is still something that is challenging, at least for modeling and for understanding the stars. So thank you so much. I wish you a good end of the day. And I thank you for having participated.
Good.
Thank you. Goodbye.
Thank you. Goodbye.
Bye.
Thank you. Bye.